Okay, good morning, ladies and gentlemen, and welcome to the lecture of today. And today we are going to dive a little bit deeper in the logistic regression models that, as I told you in the previous lecture, is one of the most widely used examples of the GLM family, together with the linear regression. And today we are going to see a number of interesting issues that are related to the use of these models. We are going to see, well, how we can evaluate if this model is actually performing well. We know that models are ultimately a huge simplification of reality. So when we use models, we are trying to establish some kind of mathematical formalism that help us to model certain real phenomena in the biomedical sciences, in sociology, in astronomy, depends on the domain. So we assume, and this is a kind of thought that I want you to have frequently when you're dealing with real problems, we assume we gather data over in a specific problem, and we assume these data are being generated by an underlying process that can be extremely complicated, but we assume, and that's an assumption, that this underlying complicated model process can be modeled using some kind of a stochastic model. And a stochastic model, for instance, a GLM, what we do is, well, we assume that we can model that with a probabilistic distribution, and this distribution, this probabilistic model, we specify it into steps. In the first step, we specify what we call the systematic part of the model. So we specify the average, the mean of this model. And in the second stage, we try to describe how these observations are going to fluctuate around the mean. And if you specify a binomial model in the second part, and you use a logistic lean to specify the model for the mean response in the first part, you get the logistic regression model. But let's see an example. Here we have the animal experiment. You know already the setting. This is some kind of toxicological study. They use 11 different doses, ranging from 0 to 20. These are the different doses of this chemical, of this drug that they were studying, and they assigned 20 mice to each of these doses. And they waited for a period of 14 days, and at the end of that research period, they counted the number of animals that had been sick by the end of the study. This is a very typical type of a study you do when you are developing a new drug, and well, one of the first phases is to use it in animals. It's called preclinical studies, and you're trying to determine the maximum safe dose. So what is the maximum dose that it can use before I induce harm in a large proportion of the population? And we knew that, well, we fitted a linear model with it in the previous lecture where we were trying to develop the first GLM. And we realized that if you try to fit this with a linear model, you will get into trouble because it will predict probabilities for doses of 20, you will get probabilities that are above 1. So we solved that problem just by introducing the logistic regression model. But well, here you have the R code. What happened if you try to use LM, if you try to use a linear model for the expected value of the response? That's exactly what we did with linear models, but the expected value of a binary outcome is a probability. And then we saw that you run into trouble. That if you do that, then simply you get values for doses of 20 or larger, your model will predict probabilities that are clearly above 1. And that is obviously not possible. Probability should be bounded between 0 and 1. So the solution for that was just to go away from the linear model and then to enter this new realm of research that we call it generalized linear models, GLM. And if you do that in R, you need to use not the LM function, but the GLM function, generalized linear model. Now, this is binomial data. What we have here is group data. And if you go back to the slide in which we described the experiment, here you have it. So you have different levels of doses that are given over here. But now at every dose, you have repeated observations because at every dose, you have 20 mice. So Now we are in the setting, it is not the Bernoulli setting, which for each outcome, your response variable here is y, 0 or 1, sick or not, is given over here, but your covariate, your explanatory variable is x, which is a continuous variable. Doses in principle are continuous, but we only study 11 different levels of this variable. So your x variable here can be interpreted as a continuous variable, and then you can do more like a regression type of analysis, or you can interpret it as a categorical variable, and then you have more an ANOVA setting. In this study, we are going to use both interpretations. We are going to consider x a continuous variable when we are fitting the model, but then we are going to somehow use the experimental design in which we only consider these 11 doses more like a categorical variable when we are going to do model checking. But for the moment, this is my x variable, and obviously at each level, I have repeated observations. I have 20 mice per level. So here you have, we are going to fit this using GLM, and this is the way you pass to R your response when you have data like this, repeated data. So you can see here, as you can see here, we have the cbind function, which is a function that binds columns. C from column and bind from binding. So you have cbind here, and you pass as your response variable two different elements. Sick, which is the response, is actually how many animals got sick at certain doses, and then trial minus sick. In this case, trials is the number of animals you had at each dose, that's 20, minus sick, so this will be the number of successes over here. This will be the number of failure over here. Now we're using successes and failure in a loose way because success means got sick and failure didn't get sick, but you know what I mean. So you pass the number of ones and the number of non-ones if you want. And you model this as a function of your response, your covariate here, which is going to be dose, and we are considering here as a continuous variable. And then you formulate, well, what is this first part here of the model. What you're doing is the first step in GLM. Specify a model for the systematic part, for the mean of your response. That's what we do in the first part. And here in the second part, in the family part, what we are doing is the second step. If you want a mixture between the second step and the first step. The second step, because we specify that this is binomial data, we have repeated measurements, but then you have here the logic function, and you're telling R, from all the possible links I can use to link the mean of the variable to the linear predictors, or if you want, from all these response functions that can use to link the response to the covariate. So mu as a function of the covariate, the link give you the link of the mu equal to the linear predictor. From all the response function, I want to use the speed function, which is the inverse of the logistic. And once you do that, well, R can start running the whole inference machine. You say here, where are your data? R will run all the inference machine. It will go there. It will make the likelihood. It will maximize the likelihood using Newton-Raphson, which is in this case the same as feature scoring. Why? Because we're using the logic link, and this link is a special. It's called the canonical link, and we know that if you feed your model with the canonical link, the feature scoring and the Newton-Raphson methods are going to be the same, and you know you're going to have a maximum and only maximum to your likelihood, and you know that you are going to be able to find this maximum. The maximum likelihood exists and is unique. And then R will feed all that, will do all that after the screen, and will put the fitted object here. And once you have that, you can ask R to give you a summary of the results. And here you have, this is now your maximum likelihood estimator for the intercept. And here you will have the maximum likelihood estimator for the fed of dose for beta. And as you can see, is positive. That essentially means that the higher the dose, the larger the probability that these animals will get sick. You have then here these elements that until now we have seen them, but we have not interpreted them. You have this null deviance, whatever it is, you get these values over here, and you have the residual deviance, whatever it is. You get here a value, and you have the degrees of freedom. We are going to finally today understand what these values are. And then you have this AIC, the Akaike information criteria. Okay, we have not gone too much into it, but we will devote some time to this later. And this belongs to the fourth school of thought in statistics, which is the information theoretic approach. It's these four big philosophical schools in statistics. We have talked about that: the likelihood school, the frequentist school, the Bayesian school, and the information theoretic school. And depends on where you are. At least personally, I would prefer to use one or the others, even though there are people there that claim, they have very strong positions about it, that you should only be Bayesian or you should only be frequentist. And here you have the number of times your algorithm need to iterate to find this maximum, and it was 4 iterations of the Fisher scoring methods. So use this expected information matrix, which is equal to the observed information matrix, because we are dealing with the logic link over here. Fine, now that you have your fitted model, then you can start trying to interpret better the coefficients. We know the effect of dosing was positive, so the larger the dosing, the larger the probability of getting sick, but you can quantify that in a different way, because if you exponentiate the coefficients like we are doing over here, if you exponentiate them and you exponentiate the associated confidence interval, then you see that the increase of 1 milligram in dose implies a 30% increase in the odds of being sick. So just 1 milligram more in doses, and the odds of getting sick has been increased by 30%. And you may say, well, what about increasing in 2 milligrams? But if you increase the dose in 2 milligrams, and here is the R code for that, well, you see that the odds of getting sick is increased almost 70%. It's increased by 69.5%. And here you have the confidence interval, which essentially tells you that if you increase the dose by 2 milligrams, the odds of getting sick is increased to between 48% and 98%. So it's a huge increase in the odds of getting sick by just increasing the doses by 2 milligrams. And if you increase the dose by 5 milligrams, then you see that the odds explode. You have almost 4 times the odds of getting sick is almost 4 times higher for somebody that has a dose that is 5 milligram higher than the one that doesn't. And actually, the confidence interval tells you that an increase of 5 milligrams in dose is associated between it, let's say almost between 3 and let's say 6 times higher. So the odds of getting sick increases by between 3 and 5 times more. So there is a very strong dose effect with this substance. When you make an increase, you are really seriously increasing the odds of getting sick. And this is the code to get this nice graph over here. So you have the linear model, the results of the fit you get with the linear model over here. In certain range of the data, the model doesn't do that terribly bad, but you clearly see that when you get to the streams of the data, especially to the right, to doses that are 20 or larger, the model goes bananas. You start predicting things that cannot be, whereas the logistic model stays nicely under the asymptote of 1, and it will never pass 1. It will always give you valid values for the probability. Okay, now a couple of new concepts here. In pharmacology, this is actually a study that is when this type of studies are typically called toxicological studies. It's done in pharmacology. As I told you, it's the first step when you get a new compound in a pharmaceutical company and you have the intention that this compound may end up becoming a drug to treat certain disease. The very first step in research is trying to guarantee the safety of this compound. And I have been surprised now when in this present situation with the COVID pandemic, how little people know about how medicine gets into the pharmacy. I mean, there is a lot of misinformation out there. People say, well, I don't want to vaccinate because nobody knows the long-term effect of the vaccines and all these things. And when you hear this type of comment, you realize that we live in a society which is highly technological, but where scientific culture is rather low in the general population. It's a pity because it creates all sorts of problems. So it follows a very long path, a drug. In the moment it is just a compound in certain labs somewhere in a pharmaceutical company, to the moment it finally can be commercialized. It's probably one of the most regulated industries in the world. I don't think that any other thing you use in your daily life is tested so rigorously and for such a long time as your medicines. So as I said frequently when I talk to friends, if you use cosmetics, if you use supplements, if you take just vitamins, I mean, everything you use in your daily life, from your cosmetic to your food, none of that has been tested so carefully as your medicines. Believe me, takes about 15 years to put a drug on the market, and 90% of all the compounds that are potential drugs, 90% end up in nothing. They just fail at certain moment during this evaluation process. And by the way, pharmaceutical companies then lose their investment. If you are investing already millions of dollars and at one of the latest phases your drug failed, you lost your investment, all of it. And those drugs that finally managed to pass all these tests and get into the pharmacy, they do that at a huge cost. It costs around $2 billion, the whole process. It's a lot of money, it's a lot of research, and it's a long time. And one of the first steps is to evaluate the toxicology of this compound. You want to make sure that this is safe. And if I have to use it, what is the maximum dose I can consider before I start giving this to humans? And that's the type of study we saw today. Now, in pharmacology, they talk about the effective level of a drug, and EL. And if you want, is the dose of a drug that produces certain biological response, right? If I'm going to use a drug, dose is everything. I can give you a poison. If it's enough diluted, it will not do anything to you, right? It's about dose. And well, you typically want to find, one of the two things you want to find here is what we call the EL50, but also the LD50. The EL50 is what is the dose that produces certain biological response. What is the minimum dose I have to use if I want this drug to do something? Obviously positive. I want this to have a positive effect. Now, they typically use the median as a value, and because you have biological variability, obviously, if I use the same dose with a person A and person B, I'm not going to get exactly the same response. People vary. So they talk about the median effect level, EL50, and that's the dose that produces a quantile effect, all or nothing, because we are assuming that we are dealing with a binary outcome, response yes or not, in 50% of the population. So if the drug has an EL50 of 10 milligrams, that means that if you apply it in the population with that specific doses, you may expect a response in 50% of the population. Now, that can be a positive response because that's what you want when you're developing a medicine, but it may be also a toxicity because every single drug produces a toxicity. There are always adverse effects. As a friend of mine that works in the pharmaceutical industry told me one, and it's completely right, a drug that doesn't produce any adverse effects doesn't produce any effect at all. So at the end of the day, is just finding a balance between the toxicity you will get and the benefits you will get. And when that balance is, where that balance is, depends on how serious is the disease, or if there are other alternative drugs there, depends on medicine. But then in the toxicity part, in the toxicological study, you also talk about the EL50, and is the doses of the drug at which you will get certain toxic effects. It can be death. It can be death in 50% of the population. When it is death, they call it LD, lethal dose. So what is the dose of this product that will kill 50% of the population? And that's called LD. Of course, when we are talking about this, we never talk about humans, we do animal experiments. And I know there are people out there that these animal protection societies and groups, and all power to them, I understand what they are trying to do, but I mean, we really need these studies before we give this to people. We really need to see what happened to animals. And of course, any extrapolation is limited, but it gives you an idea about the range of those you need to use when you move from the animal studies to doing for the first time experiment with humans, because that's what you do when you develop a drug. You do experiments with human beings, and by the way, there is not another possibility. And thanks to that experiments, we have saved millions of lives in the last century, creating very nice and powerful drugs. So what we have here, we are to concentrate now in the LD50. So this is the drug, the dose of the drug in which you produce a certain toxic effect in 50% of the population. LD comes from lethal dose, but of course, many times it's not death, it's just certain toxic effect that you really don't want, you want to avoid. So what we have here is our response variable, which is binary, 0 or 1. That toxic effect was present or was not absent of present of the toxic effect at certain doses of the drug, call it X. And then you can fit this very simple logistic regression model. So you're using the logic link, and the logic of the probability of having this toxic effect is described as a linear function of the dose. Now you can do a couple of very simple mathematics, because now what you want to know is what is the value of X over here, the dose that will produce this toxic effect in 50% of the population. So what you want to know is the value of X that will produce that this probability will be 1.5. So 50% of the population will suffer this toxic effect. And if you do a little bit of math, the steepest slope, of course, when you get the effect in 50% of the population, and you can find that this is the LD50. This is the value of the dose for which you are going to get this toxic effect in 50% of the population. Now, that's it. This is called the median effect level, or if you want, the median lethal dose, if you're talking about toxicology. And is a very simple mathematical operation. Here it is. This is what you want. The problem is, of course, that neither beta 0 nor beta 1 are known from the are known. These are unknown parameters. You need to estimate them. And once you estimate them, then you get an estimate for the LD50, the drugs that will kill 50% of the population or will produce a toxic effect there. Now, there are two ways of doing this in R to estimate this LD50. One is using the function dose P from the library mass. We are going to see that in a few minutes. But another possibility is to use the library boot, which is for it's an implementation in R of one of the most interesting ideas in statistics. It's an idea that I really like. It was developed by Efron at the end of the 1970s, and is the idea of bootstrapping. Now, we do not have the time to go into that in all details, but it's such a useful idea that I decided I will put here one slide to explain to you what is bootstrapping and how we can use it in practice, because it's really a bootstrap. Bootstrap are these things that kind of little traps that you have at the end, at the back of your boots. And the idea of calling it bootstrap is that if you are really into trouble, you really can kind of take that little bootstraps in your boot and try to pull yourself with your hand out of the problem with it. And the idea here is very simple. Suppose that you have a random sample. This is your response. In principle, this Y, this is your data. Can be whatever. They don't have to be binary. Can be binary, but can be continuous, can be Poisson data, whatever you want. So here you have your data set, the response for this first individual, second individual, and the last individual in your sample. And they are IID, so independent and identically distributed. That's a common assumption in science. We can relax that, we will keep it that. And you're going to assume that this response variable, the data generating mechanism, the real mechanism that is producing this data set over here, you're going to assume that you can model that using a probabilistic model. And that's always an assumption. But heuristically, life have shown us again and again and again that probabilistic models are pretty good to model, especially complex phenomena. But essentially that model, that probabilistic model that you're assuming that is describing the data generated mechanism, that probabilistic model depends on a parameter, theta, and typically you are interested in this guy. Why? Because your scientific questions are typically answered or written as terms, in terms of these parameters. And if you want a very good example, here you have one. So here you have the quantity of interest, which is this LD50, the dose that will harm 50% of the population. And as you can see, this parameter can be written in terms of the betas, the parameters in the model. That's frequently the case. So we are interested in this theta over here. We want to estimate this theta. Now, One of the things we want to do is we want a point estimate, just a good guess of theta, but we also want a confidence interval for theta. And Bootstrap is an algorithm. What it says that if you want to estimate theta, or you want to create a confidence interval for theta, this is what you have to do. So I'm going to give you now an algorithm that you have to repeat R times. How much is R? You specify that. You can repeat this 1,000 times, 2,000 times. Like almost always, the more, the better. But depending on what you want, if you want a confidence interval, you need to do it more times than if you just want a point estimate or an estimator of the bias. It depends on the situation. Now, suppose that you are in a step I. I can be 1, 2, 3. How many times you want to do this R time? In a step I, you're going to go to your data set and you're going to sample with replacement n elements from the data. So that means that you're going to come here and you're going to take a sample of n. And you may say, but that's the whole data set, right? No, because you're going to do that with replacement. So that means that you're going to select y1, for instance, is a possibility. You do that randomly. Maybe you will not start with y1. You're going to select y1 and you're going to put it here. And now you have the first element in your sample. But you're going to put y1 back. So now you have a y1 selected, but y1 is still back in your data set. Then you randomly select another individual. Let's say you select over here yn. You take it out and you put it in your sample. And now you have the second element in your sample. And then put yn stay in your pool. Then you go back and you select another element. And like that. But can be that you selected y1 2 times or that you select yn 3 times. That's why we say with replacement. So you take this way a sample of n individuals, n elements in your sample with replacement. So every time you take somebody, you take it in your Bootstrap sample, but you make sure it is back again in the pool. It's like if you duplicate it. I have it, but it's again in the pool. I select it again. And once you have this sample of n elements, you calculate your statistics t. By the way, you have an statistic to estimate theta. We call it t of y. And then you calculate the statistic. And then you come back here and you do that again. Another sample. Here you have the first statistic t1. Another sample, you calculate another t. And then you get your t2. And then you go back again here. You select another sample and you calculate another t. And you calculate your t3 and so on. So by the end of the algorithm, if you repeat this r times, then you will have r replications of your statistic, the one you're using to estimate theta. And now based on these R replications, you will be able to calculate the confidence interval for theta. And how do we do that? Well, let's see how we do that. There are several ways to do that. Well, first, let's see it in R. How do you implement this in R? Well, what we want to do in our toxicological studies, we want to estimate the LD50. So that's the lethal dose 50, the dose that will induce this lethal or toxic effect in 50% of the sample. And you need to construct a function for that because Bootstrap is a general procedure. This time I want to calculate the Bootstrap confidence interval for LD50, but you may want to do something different. So you need to write down what you want to do. And as you can see, you do that by writing a function in R. Here you have the function. You need to pass a formula. That's the formula you're going to use in the model you are using to describe the data generating mechanism. In this case, it's a logistic regression, but maybe something else. Maybe it's a gamma regression, a Poisson regression. That's the formula in your model. Then obviously you need to pass the data set you are using, and then you need to pass a variable that is called indices. And you're not going to do so much with it. This is just the variable that R is going to do to sample with replacement the first data set of size n, and then to go back and to sample another data set of size n with replacement. For that, you need the index. The first step over here, what you're doing is you're doing the sample. You're just sampling now n individual from your original data set. And remember, your original data set was data. So here you have data. And I'm selecting my Bootstrap sample because I'm using indices here. And then the comma, and here you're considering then all the variables in your data. So this very first step here is you're selecting your Bootstrap sample. As simple as that. This is a function that we are going to use later on when you start the Bootstrap. Now we are just writing what we want. to estimate. Then you fit your model. You fit your model with which formula? Well, the formula we saw before. Here we're going to fit our logistic regression model, and then family logic, and then with which data, not the original data, the bootstrap sample data, the one you created over here. And now in the last step, you say return, you tell it to R, give me back what I want, and I don't want this model, I want the ratio of the intercept and the slope. And that's what you're doing here in this. You are creating now the LD50. That's what you're doing in this final step. Minus, because it's minus, beta 0, the first coefficient in your model, divided by beta 2, the second coefficient in your model. So this function over here essentially takes the data set, takes the formula of the model, and will give you back the value of LD50 for the bootstrap sample. That's what you're doing. Okay, now you created the function. How we do the bootstrap? For that, you use the boot function, boot from bootstrap. And you pass the model. This is the model, the original model you used to fit the data. Now here you pass the function, the one you created over here, telling R, well, based on this model, this is the function of the parameters I need, right? We write it down. Here you pass the R. How many bootstrap samples you're going to use? 1,000. Computers are now extremely fast. You could use 2,000, 3,000. It's very fast. And now you're giving the formula R is going to use here to fit this GLM. And the formula is the formula we use at the beginning to fit the model. So it's just the number of animals that got sick, comma, the number of animals that didn't get sick times the doses. And when you do that and you put it here, you have now here all the bootstrap analysis. And for instance, if you do this head over here and you ask T, what you get over here are the different values for the LD50. For instance, for the very first bootstrap sample, you got a lethal dose 50 of 5.30. For the second bootstrap sample, you got a doses of 5.5. Here was a little bit higher, 5.75, etc. Here was around 6.7, etc. These are the bootstrap samples of LD50, the ones you obtain. You can do now all sort of things. You can construct, for instance, a histogram of your bootstrap samples. And you know that even though it looks like rather symmetric and normal at this side of the graph, you see that there is some kind of extra weight in this tail. And you see that also here. So there is some kind of tail in the left side of the distribution. Here is pretty much okay, like you can see, but indeed there is some kind of heavy tail around here for the LD50. And in general now, you can ask for confidence intervals for LD50, and the boot function in Bootstrap, you need to use here the boot CI, boot confidence interval. You just pass the Bootstrap object index equal to 1, and you put here type all, because it gives you 5 different type of Bootstrap's confidence interval, but I put all just to show you all of them, and then you specify the confidence level. So this function will give you 5 types of bootstrap: the normal bootstrap confidence interval, the basic, the percentile, and the so-called BCA. I will give you some ideas of what these intervals do. The first one over here is called the normal bootstrap confidence interval. It tells you that the LD50, the lethal dose 50, the median lethal dose for this compound is around between 3.8 milligrams and 6.9 milligrams. What is that normal? This is a typical wild confidence interval. The one we show you at the end is the typical wild, so you get your estimate minus plus the percentile of a normal distribution times the standard deviation. There is a little correction here, the bootstrap procedure correct for bias. If you use just the normal bootstrap procedure, you will see that is slightly different, but is more or less like a wild confidence interval. The one here, the percentile confidence interval, you see that it's different from the previous one we saw here, slightly different. It just takes the relevant percentile. So you now organize all your bootstrap samples and you take the corresponding percentiles, 1 minus alpha divided by 2 to the left, and 1 minus alpha divided by 2 to the right, and then this is the 95 confidence interval, because this is the probability that you will be towards the left, and this is the probability that you will be toward the right. So in the middle, you have 1 minus alpha. And that's what you get with the percentile. It's just that. Now, the second one is, or the third one is called the basic confidence interval. And why they came out with this, you see that the numbers vary again a little bit. The problem is that the percentile confidence interval, the one we saw before, performs poorly when you have weird tails, you know, when the distribution of these bootstrap samples really have kind of weird tails. And then the basic, also called sometimes pivotal or empirical confidence interval, is more robust to this type of tail issues. And that's why you have the basic there. And then finally, you have this BCA, which is bias, it comes from bias corrected accelerated interval, and it requires to use certain specific percentiles of the bootstrap sample, not the same you use with the percentile function, but another one. It is a very good confidence interval. However, that's why you have so many different types, because they all have strong points and weak points. What sometimes it happens that you have like extreme percentiles in the bootstrap sample, possibly kind of outliers. And if this is the case, you have these very weird tails in your bootstrap sample, then this BCA interval can also run into trouble. And then finally, you have this so-called student size interval, but I didn't give it. I mean, you will see that R gave you this kind of warning: bootstrap variances needed for a student size interval. And indeed, to use this, you need to give R an estimated bootstrap variance, and we are not doing that, so we didn't get it. But the most used are the normal, the basic, the percentile, and the BCA. They all have situations in which they may behave a little bit unstable. You can calculate all of them and kind of get some conclusion already. The advantage of using this is that all these will be valid even in small samples. You don't need normality. You don't need normality of your estimators. Like, you don't need like these kind of asymptotic properties of the maximum likelihood. If you want to use maximum likelihood, you need these asymptotic properties. They don't need this type of asymptotic. I'm kind of be careful here, because somehow bootstrap is also asymptotic to a certain degree, but we are not going into the details. But well, sometimes also it is very difficult to work out the asymptotics. I mean, it's a very nice practical solution. And if you just want to use the classic 95% wild confidence interval for likelihood theory, well, here you have the maximum likelihood estimator, the coefficients of your model. What else you need? You need the Hessian matrix minus the Hessian matrix, so the observed Fisher information matrix. You get that here with Bikov, and is the observed Fisher information matrix, but it's also the expected Fisher information matrix, because we use the log-lin and they are equal. And now what you're going to do here is you're going to use the second, please. What you're going to do here is you're going to construct your L50 or your LD50. So here you have is the ratio of the intercept and the slope minus. And then you have this function in the library MSM. What is that? Is the delta method. You remember we use it in the inference lecture number 1. And now with this delta method, you just pass the value for the LD50. It's just a ratio of two numbers. You pass the maximum likelihood estimator, you pass the Hessian or the minus Hessian, the observed, the expected Fisher information matrix, and then you get a standard deviation for this ratio over here. You get a standard deviation over here, and now with that, just use the classical wild confidence interval. And you get that the 50% estimated confidence interval, well, this is the point estimates, 5.31, and the confidence interval will lie between 3.9 and 6.7. If you compare it with the one of the bootstrap we got here, you see that it's pretty similar. 3.9, 6.7, 3.8, 6.9. This will be the wild confidence interval with bootstrap. Why are they not exactly the same? Well, this is based on a bootstrap sample. There is always some random element to that. I forgot to tell you, but the bootstrap procedure obviously depends on the bootstrap sample. And if you remember when I introduced the concept, you select these samples over here randomly with replacements from the original data. That means that if you repeat the procedure 2 times, you will get 2 different confidence intervals due to this stochastic process. And the variation should be small. Your interval should still be the same, but they will change if you repeat the bootstrap simply because you are selecting another random sample. That's the reason why I put a seed here when I apply my bootstrap, and that implies once you fix a seed in R, means that if I repeat this code, I will get exactly the same bootstrap samples, but it doesn't have to be the case. So essentially, this wild confidence interval we constructed at the end is very similar to the ones you get from bootstrap. The difference comes from the sampling and comes from this bias correction that the bootstrap does. So there it is. This is my confidence interval. Before going into that, there was a little detail I wanted to show you and I wanted to discuss with you. Sorry, but I forgot to tell you in the previous lecture. So if you have here, for instance, let's put in this slide. If you have here the effect of dose is positive, that means that an increase in dose increases the probability of getting sick, having this toxic effect. Here you have the standard deviation. We know from that comes, that's the root square of the second element of the expected information matrix. It's just the variance of the maximum likelihood estimator, asymptotic variance. But look at here, you have a p-value. That p-value is highly significant, so it means that there is an effect of dose. Is certainly, if you add dose to a model that only has the intercept, you have improved substantially your model. But have you realized that when you do the logistic regression, you get a set value? Didn't call your attention. When you do a linear regression, if you go back, you use the LM function, which is a GLM. It's a special case of GLM. You don't get a set value, but you get a t-value, right? You get a t-value. So when you're doing a logistic regression, when you're doing a linear regression, R uses a set value in your coefficient tables. Whereas when you're using a linear regression, R uses a t-value to calculate this test. Now the question is why? Why when I'm using a GLM, which is the linear model, R gives me a t-value, a t-score, and then a p-value based on a t-test. Whereas when I'm using logistic regression, and you will see that in other models as well, then R gives me a set test based on set scores, kind of. Why? And that's a homework. We are researchers, so I expect you to be able to go to internet, Google Sense, because when you go out there and you become a professional statistician and you work for a company, people will expect you to do that. So I really expect that you will do that too. It's not that I'm telling you that you cannot ask me, but I mean, when sometimes I get a question from you and if you see that if you Google it in the first page, you have the answer, I get a little bit disappointed because we should be researchers, right? So we should be able to go there and try to find the answers. And if you try and it's complicated and you don't get it, then you can ask me, of course. But I want to, to plant in you this seed of curiosity and this ability to go out there and try to solve problems, because that's what a statistician is. It's a problem solver. And I also want you to be able to look at details. It's another thing I hope I can motivate you to do, is try to understand the name of concepts. Why analysis of variance and not analysis of means? Why we call an estimator efficient when it reaches the lower bound of the Cramer-Rao inequality? Why efficient? Why we call something consistent? That try to understand the names, try to understand why I get a set value for logistic regression and a t-value for a linear regression. Try to understand sense. But well, now we are going to discuss another interesting topic. I told you we chose the logic link. And I also told you at the time, it is a choice. You may choose something different. And why we use the logic link? Remember the problem we had? You have a set of outcomes. You assume that these outcomes are being generated through a very complex biological, social, economical process. You are going to model that process using a stochastic model. And in this case, if your outcome are binary, you want to just explain why some people respond, some people don't respond. So you want to understand why some people get sick, other people don't get sick. And you want to study that with a covariate. Why some animals get sick and others don't get sick? That's because I'm giving them a dose of certain chemical. And then I want to understand how these doses relate to the chance of getting sick. That's what we want. And the problem is when we try to do it like in linear regression, what was what we did? We model the expected value of this response, the average response, as a function of as a linear function of the predictors. The problem is that in linear regression, this average is a number that can take any value on the real line. Can be minus 20, can be 35. And so you can model it as a function of a linear function of the predictors without any issue. But now we have a binary variable, and averages, a mean of a binary variable, is a probability. And then we realize we are dealing with a different animal here. A different animal, but at the same time, there are a lot of commonalities between linear regression and logistic regression, even though they look like two totally different animals. And we saw some of these commonalities already. The scores function are structurally the same. The Hessian matrix is structurally the same. They have the same shape. You just have to change some parameters, but for the rest, it's the same matrix. And well, you cannot link a probability with a linear predictor because you get out of range. What was the solution? What about using something called a link function? So I'm going to transform that probability in a clever way so that I did now my transform probability can take any value between minus infinity to plus infinity. And I'm going to model that transformation as a linear function of the predictors, and then I transform back and I get my probability. That was the strategy. And when we do that, we say you are modeling the systematic part of the model, the mean. And the second step is now I have the mean, but observations are not equal to the mean. They vary around the mean. And that's the second step. You put a probability model to explain this variability around the mean you specify in the first step. And that's your GLM. And we did it with logistic regression. I showed you that is essentially what you do with linear regression. And that's going to be our algorithm from now on. Now, the problem is that link function we use to connect the mean to the linear predictor, or if you transform the mean and you use this transformation to link it to the linear predictor, is called the link function. If you back transform the mean and you have now the mean as a function of the linear predictor, that's called the response function. The link function is the logic, the response function is the speed function. Well, fine. The problem is that I told you, okay, we use the logic, but in principle, you could use something else, right? Nobody says that it's only the logic. And I told you, well, the logic is indeed one more, one among many, but it's kind of a special one. First is the canonical link. What that means, we will show you later what that means. You will have to wait a little bit to understand that word, but the canonical links are special. And why they are special? Because when you use the canonical link, you have this very nice property that the Hessian doesn't depend on the response. And that means that the expected feature information is equal to the observed feature information. I mean, the minus the Hessian is equal to the expected Hessian because the expected minus the Hessian because the Hessian doesn't depend on the response. And that means that Newton-Raphson and Fisher scoring are essentially the same algorithm, and that's a good thing. The second thing is that when you use the canonical link, then the likelihood function is concave. And what does that mean? That means that the Hessian is positive definite. And what that means, well, sorry, it's positive negative. And what that means first, that the maximum likelihood exists. And second, that is unique, it's actually a maximum. So when you use the canonical link, you have convergence guarantee. Almost always, not always, almost always. It can go wrong, and it's what we call separability in logistic regression, and we discussed a little bit about that the previous time, and we will cover that in detail in the next lecture. But most of the time, the maximum likelihood exists and is unique. That's another nice characteristic of the canonical link. And on top of that, the canonical link has another nice properties, and it is that if you use the logic, you have this nice interpretation of the coefficients. The coefficients are just logarithms of odds ratios. And we kind of understand odds ratio. Fine. But that doesn't mean that the logic link is always your best choice. You may, most of the time it works pretty fine, but you have situations in which another link may be more appropriate. And I'm going to show you an example today. So what are other options there? We're going to discuss three possible response functions. Response functions, you remember, if you have that this function of the mean is equal to the linear predictors, we're going to call the linear predictors eta. That f over here is your link function. When you back transform and you get now directly the mean as a function, which is the inverse of f, as a function of your linear predictors, function of eta, now this is called the response function. So f is the link function because it's what you use to link the mean to the exponential function. F minus 1 is the response function because now you give you eta and you can find the mean. It's terminology, but it's nice to have it clear. And we are going to see three different response functions, which is equivalent to see three different link functions. Now, they all are going to have the same properties. By the way, response function for modeling binary responses. We are dealing with this kind of binary outcome. All the response functions we're going to use are bound between 0 and 1. It's no surprise because we're dealing with probability, so I want to model the mean of the data, which is essentially a probability, as a response function of the linear predictor. So obviously, whatever response function you want to use here, f minus 1, it has to be between 0 and 1, because this mu is basically a probability. So they are all going to be between 0 and 1. They all will have this nice, we call it sigmoidal S shape. They are going to be thins like the logistic, more or less. They have to be asymptotic to 0 and they are going to go to 1. It's going to be between 0 and 1. They can be like this, or obviously they can also go the other way, but they are going to have this S shape. And this last property is they all will approach 0 and 1 asymptotically. So whether you go to the right, if you go to the right far enough, they are going to get close to 1 over here, or if they have the other shape, close to 0. And the same if you go far to the left. They are going to get like close to 0 or close to 1. And they can go negative here, by the way. No negative, the probability stays between 0 and 1. This is always positive, but you can go negative in the predictors, obviously. Now, from where these three suggestions are going to come, and you can propose something else. Whatever satisfies these properties is going to be a potential response function. But these ones has an extra appealing, and they come naturally. They arrive naturally from the idea that this binary response you observe is actually a dichotomization of an underlying continuous, right? So you may think that there is some kind of underlying continuous and there's certain threshold, and when this continuous passes the threshold, the 0 becomes 1, right? So you may assume that there is some kind of basic toxicity level and giving you doses of this chemical, and your body starts deteriorating, getting worse. Your body is still fighting back. You don't want to get sick. Your body is fighting back, but I keep increasing the dose. And then there is a threshold there that once I pass it, you just get sick. Your body cannot cope with that anymore. So you can imagine that this sick, no sick situation that you observe in practice is a raw expression of some underlying levels of deterioration. When you start giving this dose, your body starts deteriorating, and the deterioration, the damage start getting accumulated. You're still okay, you still function, but you are, your body's getting troubles to cope with the problem until you become sick. And then here we have the different examples. This is the Probit model. We call it in logistic regression the Probit model, the Probit mean response function. And this is the way you can think about it. Suppose that you have a variable, continuous variable yi. We put here a tilde on the yi to emphasize that you don't observe that. It's latent. It's that continuous that you may assume. By the way, you don't need to assume that that continuous. As I said, you can use the Probit model without making any reference to this continuous, but it's nice to see it mathematically. It's a nice way of obtaining the model. But once you get your Probit model, you don't need to assume that there is a continuous variable at all. But it's a nice way to get it. So let's assume that you have this continuous random variable that follows a linear model, right? So this epsilon over here is what we call a white noise. Has mean zero and variance sigma square. So a latent variable is a variable that you do not observe. Is there, but you have not measured it or you cannot measure. It's what I say now. If you are giving this toxic agent, you may assume that this yi delta is maybe, if you want, a variable that quantifies the deterioration of your body, the deterioration of your immune system, let's say. And you are not quantifying that, but your immune system gets weaker and weaker and weaker due to the chemical. And then when it's weak enough, you get sick. That would be the yi. Latent means unobservable, unmeasurable. And then what we are going to assume is that what you actually observe, this binary outcome that is sick or not sick, is actually a manifestation of something that is going on at this unobservable latent level. So you may assume that if this y variable gets negative, this y delta, then the person will get sick. The deterioration has passed a threshold. Now it's so deteriorated that you start seeing symptoms in the real life. And before that, the person was coping with it. It was not good, but was coping with it, could function. It's not sick until the person gets sick. For instance, when you get infected by a virus, like this COVID virus, what happens is the virus enters your body and start reproducing and reproducing and reproducing. That would be your latent variable. The latent variable over here is just, if you want, some kind of viral load, how many viruses are already inside your body. When you're exposed, you're not exposed to 2 million viruses. You get a number of them. They go inside your body, they infect your cells, and they start making your cells factories that produce more virus. For the time, if it's COVID, it can be until 2 weeks. For the time, you're okay. You're fine. You're not sick. You feel good. You go around and you spread more virus because nobody knows you're sick and you don't know it yourself. That would be this latent variable. It's unobservable. You're doing fine. But when that amount of virus passes certain limits, then your immune system is overwhelmed and you get sick. It's an example. I mean, it doesn't matter. It's just an example. Now, is this this latent variable becomes negative, then we are going to set you get sick. If it stays positive, you never get sick. So the outcome you observe, this binary outcome, is just a manifestation of this latent variable. Which cutoff value you choose here, which threshold variable, that's completely arbitrary. You can always say it's 0, because if it's not 0, you can center your latent variable and you say it's 0. That's completely arbitrary. Now, the question is, what is the probability that y becomes equal to 1, given the covariance? And now we are going to try to calculate this probability using this latent structure that we assume here. As I said before, once you get your model, you can forget about this. It's not that if I want to use a Probit model, I need to think there is a latent variable. No, you don't need that. Once you have the model, you have the model, and you use it, and it works. But it's a nice way to do the mathematics. So how can I calculate now this probability over here? Well, I know when y is equal to 1. Y is equal to 1 when something like this happens. So when y is equal to 1, the probability that y is equal to 1 is essentially the probability that this latent process is going to be negative. And I have a model for this guy over here. It's my linear model. So it's the probability that this is going to be negative. And then what you do is you isolate the epsilon I here, and then you divide by the variance of epsilon I. That's what you do here, and you get this expression. And you divide it by the variance of epsilon I. And then once you do that, this part of your probability over here, that's a standard normal, right? Epsilon I divided by sigma, that follows a normal distribution with mean 0 and variance 1, right? It's part of the assumption of the latent model. So you have now, this is the probability that a standard normal variable is smaller than something. That's what you want. That's the probability. And you can calculate that very easy using the cumulative distribution of a standard normal. What is this beta p? This beta p is beta c divided by sigma. And this, guys, is the probit model. You're modeling now the probability that y is equal to 1, not using the speed function, but using the cumulative distribution of a standard normal. That's called the probit model, and it's another model that you can use the speed function, you can use the cumulative distribution of a standard model. Now, this beta p over here is the coefficient in the probit model. This beta p is just the ratio of these two parameters. Beta c, which is the coefficients in the latent model, so beta c is not observable because you don't have the latent model, you don't have the yi tilde, so it's something you cannot estimate, and the sigma, which is the variance at the latent level, you don't have any of these things, so you cannot estimate beta c, you cannot estimate sigma, but you can estimate the ratio, because the ratio, you have data for that, right? You have the binary outcome. So you can estimate the ratio. So neither beta c nor sigma are identifiable. Only their ratio. The ratio, you can estimate. Now, this model satisfies a nice property, and that is symmetric. And what we mean by symmetric is if the response variable is recoded, so if you create now yi, I don't know how to call this, yi prima, if you want, just to give it a name to this symbol here, if you reconstruct, you recode your variables 1 minus yi, so essentially what you do is the ones become 0 and the 0 becomes 1, right? What if I call sig 1 and not sig 0, I do the opposite way. Not sig is 1 and sig is 0. You just recode the variable. Then the only thing that is going to happen in your model is that the coefficients will change their signs. So what was positive will become negative, what was negative will become positive. That's it. And that's called symmetry. And that follows from this very nice property of the cumulative distribution of a standard normal. So if you use the probit model and you just change the zeros into ones and the ones into zero, you recode your response variable, you call it yi prime is equal to 1 minus yi, then the only thing you need to do is to change the signs of all the coefficients. And that is the probit model. What about the logistic model? Well, when I introduced the logistic model, I didn't talk about any latent linear model, right? The same with the probit. You can just start by using your probit model over here. You can just say, this is going to be my response function, period. My response function is going to be the cumulative function of a standard normal distribution. And that's it. You can start there. You don't need to start talking about a latent model. You don't need that. But it's nice to see it. And actually, the logistic model that I introduced like that, we're going to use the logit link. We're going to transform the probability using the logit link. But you can also look at it as the manifestation of a latent process, exactly in the same way. Suppose that you have, again, this latent variable that you cannot observe. And suppose that this latent variable satisfies, again, a linear model. You don't need to do that. But I'm just doing it for illustration purpose. But now the error term, this epsilon here, they are not going to be normal distributed. They are going to follow a logistic distribution. Oh yes, there is something called the logistic distribution, like you have the normal distribution. A logistic distribution with variance sigma squared. And this latent process will lead to the logistic model. Now, you can show that the cumulative distribution for a logistic random variable with mean 0, because we are going to assume this guy here is still a kind of white noise, white noise, if you can show that if a logistic random variable has mean 0 and a standard deviation like this specific standard deviation, then the cumulative distribution is going to be, guess what? A speed function. So if you have a random variable like this epsilon over here, they have mean 0, is logistic distribution, mean 0, and variance pi divided by root square of 3, then the cumulative distribution of this guy is going to be the speed function. Now, we are not assuming that the variance of this guy is this. We are not assuming that. But we will use it later. The variance is just sigma squared, whatever it is. Now, how can you calculate the probability of observing an event now? Well, The same way, y is 1 when this guy is smaller than 0. So let's calculate the probability. The probability that you will observe an event is the probability that the latent process is negative. You can always recode your variable, your latent variable, to get this threshold, always. So what is the probability that this is negative? What is the probability that the linear model is smaller than 0? And now we are going to do the same thing. We are going to pass this to the right side, and we are going to rescale the epsilon to get something with variance pi divided by the root square of 3. Now we want to get this variance to be able to use this cumulative distribution. So the only thing you do is you pass this to the right, and then you divide the epsilon by sigma to get variance 1, and then you multiply it by pi divided by the root square of 3 to get the right variance. Once you get that, then the probability that this is equal to 1, which is what you're trying to answer, is equal to the probability that this element is smaller than this. Now, this element over here is a variable that has a logistic distribution with variance pi divided, standard deviation pi divided by the root square of 3, and we know that the speed function is the cumulative function. So now here you have, this is the response function of a logistic model. That's it. And who are these beta L? Who is this beta L? Well, this beta L is calculated over here. Here you have the value for the beta L. So the beta L is given here. Now, if you remember how we did this when we used the Profit model, the Profit model, the coefficient of the Profit model was just this part, the coefficient of the latent model divided by sigma. And now we get this extra term over here. So it is just one, the coefficient for the logistic model over here is just minus, sorry, 1.81, the beta L, the beta P, the P you got from the Profit model. There is a relationship, an approximate relationship between the coefficients you get from the Profit and the coefficients you get from the logic model. Now, again, beta C is not identifiable. Sigma square is not identifiable. These are parameters of the latent model, and you never observe this latent variable, but you can identify their ratio, because their ratio is here. This is the coefficient of a logistic regression, and you can use maximum likelihood machinery to identify that. Now, the logistic model is also symmetric. And that means, again, if you change the zeros into ones, if you construct a new response, which is yi prime equal to 1 minus yi, what was coded 0, now is coded 1, what was coded 1, now is coded 0. If you do that, the only change in your model is the signs. Now you need to all the coefficients to multiply all the coefficients by minus 1. But it's positive becomes negative, what it's negative becomes positive. But for the rest, the interpretation is the same. Now, there are other choices as well. For instance, you can use in R something called the log-log, complementary log-log mean response function. I'm not going to go again through all the details. The distribution you're using in this case is called the Gumbel probability distribution. And it's a distribution that you use to model extreme values in nature. So a third mean response that you can use is sometimes called the complementary log-log function, is when the error in your latent model follows a distribution that is the Gumbel probability distribution. An important thing now is that when you model the error using a normal distribution in your latent model, the normal is symmetric. When you model your error using a logistic distribution, the logistic is symmetric. When you use the Gumbel distribution, that's not symmetric. So now you're modeling the error terms in this latent model with a distribution that is not symmetric, and that has an impact on the observed binary data. You will see that now you will get a model that is not symmetric. Remember that when we say symmetry before, it has two interpretations. First, the distribution you're using at the latent level is symmetric, but at the observable level, the impact of that is that if you made the ones 0 and the 0 ones, if you construct a new response y that is 1 minus y, the only thing that happens is that the signs in the model changes. The signs changes, but for the rest, the values stay the same. Now, if you use a non-symmetric distribution for the latent level, like when you use this Gumbel probability distribution, and at the visible level is the complementary log-log, then the symmetry is gone. You are not going to get this property that changing the ones into zero just change the signs in the model. It's more complex than that. So here you have at the observable level, what you do is now the transformation you use for your probability. Here is your probability. This is what you're trying to model. That you're trying to link that with the linear predictor. That transformation now is not a logic transformation. It's not a probit transformation. Is a log-log transformation. You calculate the logarithm of minus the logarithm of 1 minus the probability. And this is now the logic. Sorry, the link function. This over here, this complementary log-log. Why log-log? Because you have 2 times a logarithm. You have the logarithm here and you have the logarithm here. That's why log-log. And why complementary? Because you don't use the probability, but 1 minus the probability. And from there comes the name complementary log-log. That complicated transformation over here is what you link with the linear predictor. What is the response function? Back transform. So here you have now the response function. This is the way to get now the probability based on your linear predictor. It's not anymore the speed function. It's not anymore the cumulative distribution of a normal, standard normal distribution. Is something more complex. And this is the result of assuming a Gumbel probability distribution for the errors at the latent level. And now symmetry goes out of the window. You don't have this property anymore. And the last one we are going to see is the log-log mean response model. Another log-log mean response model. And what happened here is that it's very similar to the complementary log-log, because you have here the log and you have minus log here. Exactly the same with the log-log. You have log and you have minus the log. But now we don't talk about complementary log-log. We don't talk about the complementary log-log link function, but just the log-log. Why not complementary? Because now we put here directly the probability. Whereas in the complementary log-log, we put 1 minus the probability. It's very similar, but it's different, and we are going to see the difference. And this is just, guys, another link function I can use. Instead of using the logic of using, this probit type of link function, or using the complementary log-log, we use just the log-log. And now this is what I equal to the linear predictor. What if I want the probability directly? You back transform. And this is your response function now, and here is your probability. And these are all possible ways you can link your mean to your linear predictors. I started with the logic because it has these very special properties, but there are other models out there. Now, the logic has many advantages, but sometimes these other links functions may work better. Now, the symmetry property goes out of the window. You don't have anymore this property that if I make the zeros becomes 1 and the ones become 0, I just decided that now 1 is not going to be sick. Now 1 is not sick and 0 is sick. If you do that, then it's not just changing the signs in your model. If you use the logic model, the only thing you need to do is to change the sign. If you use the probit model, the only thing you need to do is to change the signs. But if you use a log-log model, you use the log-log link function, now that property goes out of the window. Now, the interesting thing, one of the interesting things about this link is that suppose that x is just a scalar, like in the animal experiment, x, the variance is just those, it's just a scalar. Then if beta is positive, the model is monotone decreasing. So the larger the x, the smaller the probability of observing the toxic effect if beta is positive. And if beta is negative, then you get a monotone increasing function. That means that if beta is negative, the larger the dose, then the higher the probability of having the toxic effect. And this is just a property of the response function, the link function you're using. But these are different models. Now, what are the practical differences between these models? You may think, well, if I'm now in a data set, like for instance, the animal experiment, which one should I use? Should I use the logic just because the logic has this nice interpretation, this computational advantage, or should I use another one? I mean, how I decide this? Well, there are some practical differences between them. Let me tell you this, the probit and the logic typically give very similar results. It's not the same model. The parameters in the probit model cannot be interpreted as logs of odds ratios, and that's a disadvantage. The probit model, the parameters don't have this nice interpretation in terms of association. That's one of the reasons why we love the logic, because you have this, you can say an increase of 1 milligram in dose represents a 39% increase in the logs of getting sick. And that's in the odds of getting sick. And that's a nice interpretation, right? If you feed a logistic regression model, you can say that an increase of 1 milligram in dose is associated with a 69% increase in the odds of getting sick. If you use a probit model and you get a parameter there for dose, you cannot give that interpretation. I mean, if it is positive, you know that the larger the dose, the larger the probability of getting sick, but you cannot have that interpretation. So that's a nice thing about the logic. But the logic and the probit typically will give you similar results. But if you use the complementary log-log, or if you use the log-log link, these models are telling you a different story. Now, what is the difference from a practical point of view? Well, I told you, the normal distribution is symmetric. When you're thinking in terms of the latent model, you're putting this symmetry in the errors. The logistic distribution is symmetric. When you think about the latent model, you're putting this symmetric distribution around the error. And symmetry means you have the same pattern to the left and to the right. And when you then go back to the binary data, symmetry means that if you change the zeros by 1, you only have to change the sign. Now, what this means actually? Symmetry actually means that the curve for the probability, which is the probability of getting sick, let's say for a given dose X over here, that this curve is also symmetric. Symmetric about which point? Symmetric about 0.5. So if you use the logic link, or you use the probit link, you are getting a curve for your probability that is symmetric around 0.5. And what do you mean by symmetric around 0.5? Well, the curve, the probability of the event will approaches 0 and 1 at the same rate. So you are assuming that you have this dose, and if dose goes to 0, the probability that you will have no disease, right? And if dose goes to infinity, you have the probability that you will get sick. Well, you expect that if you go, the doses increases to infinity, that the probability of getting sick will go to 1. And if the doses go to 0, you're not giving anything to the mice, you expect that the probability of getting sick will go to 0. Well, if you use a symmetric model like the logistic of the probit model, the speed at which these functions go to 0 and 1 is the same. That's what I mean. They goes to 1 and they goes to 0 at the same speed. And that doesn't have to be the case. That doesn't have to be the case. Increasing the doses may increase the probability of toxicity much faster than decreasing the doses will decrease the probability of not getting sick. This curve may go to 1 and 0 at different speeds. If you use the logic model, if you use the probit model, you're assuming that they go to 0 and 1 at the same rate. And this is what happens when you use the logic and the probit model over here. Now, if you have a situation in which that's not true, in which these phenomenon, when you increase the doses, goes to 1 or goes to 0 when you decrease the doses, not at the same speed, then the logic model and the probit model will not be appropriate. Now, for instance, the complementary log-log, this one that uses the Gumbel distribution for the latent processes, it produces an asymmetric model. Now you will not go to 1 and 0 at the same rate. Actually, you will approach 0 fairly slowly, and you will approach 1 sharply. So if you use the complementary log-log, actually that will be good to describe in a process where when you decrease the dose, the probability of not getting sick goes to 0, but smoothly, quite softly. But when you increase the doses, you have really a very toxic agent. Decreasing the agent, the dose, people will not get sick, but slowly. It really takes a time to get to 0. Whereas increasing the dose sharply goes the probability to 1. Makes the probability to going sharply to 1. It's a very toxic agent. That would be the complementary log-log. And the log-log, the normal log-log, induces the opposite asymmetry, right? Now, when you decrease the dose, you will approach zero sharply. So if you really start giving less substance, the the probability of getting sick will reduce very, very sharp. And when you increase the dose, people will get more sick, but slowly. The toxicity will increase slowly. And if you have that situation, then you may want to consider the log-log link. So it's important to know this, because even though the logic model is the most frequently used model, there may be situations in which you want to use something else. So here you have, I'm going to fit all the models now for the animal experiment. Here you have the logistic model over here. The logistic model is just to consider here the logic link. I'm going to use the probit model. I call it LSIC. PSIC is when you use here the link probit is implemented in R. The GLM has both options over here. And now I'm going to use the complementary log-log link, is the one you just do that by putting in the link part of the GLM called C log-log. But there is a problem. The log-log link, which one I would like to use, is not implemented in R. So if you are just a basic R user, you will be tied up with these three options: logic, probit, and C log-log, because R doesn't have the log-log. But if you are a little bit of an advanced user, that's not a problem with you, because you will be able to write down the link yourself. Now, I did it for you. Here you have the function to implement the log-log link, not the complementary log-log, but the log-log. Remember, the log-log accounts for the fact that you go to zero fast, but you go to one slowly. So you have a toxic agent that if you reduce the doses, people dramatically decrease the probability of getting sick. Whereas if you increase the doses, that increase the probability of getting sick, but slowly. That's the log-log. And here you have how to do it. You can now, if you want to implement another link, it's quite trivial to follow this step. I put some notes here so that you know what each step is doing. Guys, study it yourself. And then you need to do a little bit of specifying your link over here. But essentially, once you do that, you can just fit the model you need. I'm not going to the details, but now you give just the GLM function and you pass the log-log v, and this is essentially the link I created. That's a log-log link function. And I call this LLSIC, log-log link function. And once you fit that in R, these are the results you get. And for instance, here you have the probit model, and these are the coefficients for the probit model. And I told you that the coefficients of the probit model are related to the coefficients of the logic model, approximately. So the coefficients in the logic model, which are the ones we have over here, these coefficients can be obtained as 1.8 the coefficients in the probit model, approximately. And if you do the math, you see that indeed, here is it. This is very similar to this guy over here. So this is the coefficient in the probit model. And if you multiply that by 1.8, you get something similar to the intercept in the logic model. And here you have the coefficient in the probit model. And if you multiply that by 1.8, you get something similar to the coefficient in the logic model. That's why logic and probit in general, they give you similar results. And here you have the complementary log-log. And well, here you have the result for the log-log. And you see that consistently you get a very significant p-value. So respectively of the model you use, it's clear that those is having an effect. Now, okay, look here, the log-log give you a negative coefficient, whereas all the others give you a positive coefficient. Why is that? Don't panic. It's just that, remember, the log-log have this, the monotonicity change, the asymmetry change. So when you have a negative value for the log-log, it just means that when you increase the dose, the probability of getting sick goes to infinity. When it's negative and you decrease the dose, the probability of getting sick goes to zero. It's just a property of the model, is nothing apart. But they have a different interpretation. And by the way, these are symmetric. You get this symmetry. These ones are not. And symmetry means that if you change the zero by ones, you just need to multiply by minus the coefficients, and there is the new model. Here, you don't get that. Symmetry also means that with these two models, you go to 0 and to 1 at the same rate. Whereas here, you go to 1 sharply. Sorry, you go to 1 sharply and you go to 0 slowly. And here, you go to 0 sharply and you go to 1 slowly. And if you plot the models, you could see the red line and the green line is the probit and the logistic. They do almost the same. Do you see? They give very similar results. Now, if you look at the complementary log-log, that is the blue line over here, it kind of misses the scene because it fits the model pretty well in this part of the graph, but here kind of miss it because look at where the points are, and he kind of go to zero too slowly. Now, if you look at the complementary log-log, sorry, at the log-log, which is the one RD doesn't have, and we've programmed it ourselves, this seems to be the best model because it really seems to follow the data. Look, it's nicely between these 2 points over here. You see the black line. The blue line gets very close to the points here, but it misses the point over here. But the log-log link seems to get very close to the points here in this tail of the distribution. It really goes to zero sharply and goes to one softly. So maybe the log-log is actually the best model here, not the logic, not the logic. And it's the one that you don't have programmed in R. Now, let's take now a couple of minutes pause, and then we will move to the second part of the lecture, which is about goodness of it. Okay, we're back. Now we are going to start little bit of a different topic, but also very relevant in the logistic regression model. And as you will see, is a topic that is the model checking topic. Is something that is fundamental when we are using statistics and we are modeling. It's something that you study in pretty much detail when we saw the ANOVA model and the linear regression model in the LM course, but is a topic that plays also a very important role here. And actually, in any modeling framework, you need to make sure that your model is actually capturing the main feature of your data. We know our model is not going to be perfect. I know I'm not going to be able to describe this complex process that is underlying the data generation completely. Reality is an extremely complex thing, and we need to simplify it to be able to get some kind of understanding. But at least my model need to be able to capture the main features of the data. So if I have a problem, like in this case, we were just analyzing, if I have a problem in which the probability of going to 0 is sharper than the probability of going to 1, and I use a logistic model, and I use a probit model, I may be missing a very important feature of the data, because this is a substance with a toxicity level that is manifest in this way. If you reduce the doses of the substance, then the probability of getting sick will dramatically decrease. It will fast, in a sharp way, will go to 0. So if you have certain doses and you observe a toxicity and you start reducing the doses, you know that the probability of getting sick will go down very fast. And at the same time, if you increase the doses, you know that the number of people that is going to get sick will increase, but it will happen in a soft way. You will not have any sharply increase in the probability of having a toxic event if you increase the dose. It's kind of soft towards this side, and is much sharper to this side. And if you have such a phenomenon and you use a probit model or logistic model, you're going to miss that. And I assume that's an important feature in the data. So how we can check the validity of our model? Now, we are going to start seeing a couple of goodness of it tests. And before doing that, let's go back to linear regression to refresh a little bit the ideas we use there. Now, like in linear regression, once you fit your logistic model, you need to assess that the model is approximately okay, that is capturing the main features in the data. And the GOF test, the goodness of it test, actually do that. They provide some kind of overall measure of the fit of the model. You do the test. If the test is not significant, that doesn't mean that your model is perfect and is the true data generating mechanism. It seems like it means that, well, your model at least seems to have a good overall fit, seems to be capturing the main players. Not be perfect, but it's kind of doing a good job. Typically, this type of tests are not sensitive to kind of if you get a poor fit for a couple of points. So if your model is kind of capturing the pattern, the trend in the data, the main patterns, but for a couple of points your model kind of miss it, well, probably the GOF test is not going to be affected by that, which is a good thing. It's a good thing. Now, we would need to make two distinctions here, and it's the same distinctions we make in linear regression. You need to distinguish between when we have replicated data, when we have the binomial distribution in the second stage of the model to describe the variability around the mean, or when you don't have replicated data. So when you are in the Bernoulli case, when you have to use a Bernoulli distribution to model the variation around the mean. Now, how we did it in linear regression. You remember simple linear regressions. You have your response and you have one univariate predictor. In this case, when you wanted to do a GOF test, you need to a requirement. You need to have repeated observation at one or more level of your single predictor X. You needed to have for every value of X several Y's. That was a requirement we had to impose when we wanted to develop a GOF test, a goodness of fit test in linear regression. If you have multiple linear regressions, so if now your X over here is not a scalar, but it's a vector, then a similar requirement was necessary. You need to have repeat observations at different levels of the predictor. So for every vector X, for every combination of covariates, you need to have different values of Y to implement the GOF. And in logistic regression is going to be exactly the same. We are going to see three different goodness of it tests. Two of them will require repeated observations. For every level, for every specific level of the covariates, values of the covariates, we will need to have several Ys to be able to implement the test. And these two tests are going to be the Pearson chi-square test, and it's going to be the deviance test. And it's when you have repeated measurements. Now, if you do not have repeated measurements, so if every level of the covariate is unique, there is only one individual in the data set, one and only one, that have these specific values of the covariates, so the covariates becomes really tailored to a specific subject, then you cannot use the Pearson chi-square test, you cannot use the deviance test. We will have something there called the Hosmer-Lemshow test. And it's useful when you have unreplicated data or for data containing just a few replicated observations. Then we need to use the Hosmer-Lemshow test. But let's start with the replicated case. Now, here, suppose that you have now replicated observations at every level of the response variable. So this is your vector of covariance. You may have there gender, race, you name it. Now, for every value of that covariate vector, you have several Ys. You have repeated data. And you can see, for instance, this is typically the case, not always. For instance, in the dose example, in the animal experiment, you have the dose covariate. And for every value of those, you have repeated measurements, because by design, at each dose, you use 20 mice. So this is an example in which you have 20 different doses. That's n over here. N is the total number of replications you have for the covariates. We have those 0, those 2, those 6, so on until 20. So we have 20 different values for the covariate. You have n, capital N, values for your covariate, 20 different doses. And each value here, for each value of the covariates, you have several replications. In the case of a study, for each value of those, you have 20 mice. So you have replicated observations. Another situation in which you may have that is when you have categorical regressors. For instance, you're doing a study and one covariate is gender and the other covariate is income, and you code income as 1 meaning high and 0 meaning low, and gender is males and females. So you have these two covariates, gender and income. How many values these covariates can take? 4. Right? You can be a man with low income, a man with high income. That's a possible value for your vector of covariate. Man, high income. You may have man with low income. That's another possible value for the covariate, man low. You may have female high, and you may have female low. So in that case, you have vector X, which is composed only by categorical covariates, can take only 4 different values. And you're going to assume, it's like in the ANOVA level. You're going to assume that each combination of these levels, you have replicated data. So when your vector X is a vector of categorical responses, what do you have is essentially like in ANOVA. You have 2 factors, gender and income. These factors have A and B levels, and then you get an A times B table. And you have replicated measurements because at each cell of the table, you have a number of observations, like in ANOVA. So when your vector X is completely categorical, you're in the ANOVA setting. And now you have A times B treatment in the ANOVA way. And at each level of these combinations, you have replicated observation. You have so many individuals that are males and have a high income. It's the same. So this type of repeated measurement situation is typically what you see when you have, for instance, categorical regressors, because then you are in an ANOVA setting, actually. And then the vector X, xi, it defines a cell in the table. And you have n vectors and different values for your covariance, because this is the number of cells you have in your table, right? If you have gender and income, you have n, you have 4 possible values for the covariance, you have 4 cells in the table. So you're back into the ANOVA setting, and what you're assuming is that in cell xi, treatment xi, if you think about treatment like in the ANOVA sense, treatment xi, this is just a specific cell in the table, a specific combinations of level of the factors. You assume that in that cell, you have ni replicates. You have ni observations Yij. So what is Yij? Is the response of subject J in treatment I. And treatment I is given by this specific combination for the covariance we call Xi. So that's it. It's like ANOVA setting. Now you may have also repeated measure with a continuous variable. Yeah, the dose, the animal experiment is example. But that typically happens when you are doing an experiment, when you design the experiment. Because if you go to real life and you have continuous variable, so if you're measuring weight, body mass, and cholesterol, and you just do an observational study and you select a number of individuals, typically you will only have one individual with 3.5 kilograms, 20.6 body fat, and a cholesterol of 3.5. Probably if you do an observational study, every value of the vector of covariance is unique. It's very unlikely that you will have two individuals with exactly the same weight, exactly the same body fat, and exactly the same cholesterol. The probability of that will be 0. So if you do an observational study and you have continuous variables, you're not going to have repeated measures, very likely. If your variables are categorical, yes, because then you have gender, female or male, income, low and high. Typically, you are going to have several females with a low income in your study. You're going to have several males with a high income. Typically, in the ANOVA setting, you will always have the repeated measurement, unless that you may have a 0 in one of the cells. May be very unlikely to have a male with a high income or to have a female with a low income. That is the case, you may get a 0 in the table. But if your covariates are categorically, typically you have repeated measurements, like ANOVA. If your covariates are continuous, if you have an experiment and you control how many doses you're going to give, you can have repeated measurements. In another case, probably you will not. So that's it. Let us consider the repeated measurements. So Yij is the response for subject J in treatment I. Subject J in treatment I. And treatment I is given by this value for the covariance Xi. And of course, the Ya now are not normal, because in another case we will be in ANOVA. They take value 0 and 1, which is success and failure. And now what we are going to do is we're going to construct the sum of all these individuals in treatment I. So Yi is the number of successes in treatment I. You have Ni subjects in that treatment, and now you want to know how many of these subjects in the treatment I succeeded. And this is your new variable Yi. And now you are in the binomial setting. So you have to construct your model. You know, you need to give 2 steps. The systematic part, let's model the mean. So the probability that subject J in treatment I will succeed, the probability that this specific subject in this treatment will succeed, is just given by the logistic model. You use the logic, you use the logic link, and you use that to link the mean to the linear predictor. You may use another link as well. It doesn't matter. But in this case, we're using the logic link. And then, okay, now I have specified the mean of my distribution, but I know the responses not all are equal to the mean. How these y's vary around the mean. Well, that comes the distribution part, the second step. And I'm going to model the variation of yi around the mean using a binomial distribution. And we know the binomial distribution has certain mean. What is the mean of a binomial distribution? Is n times pi. So what you expect, what is the expected number of success in treatment I? What is the expected number of success there? Is Ni, the number of people in that treatment, times the probability of success for that treatment. That's the expected number of successes for treatment I. And this Pi over here is given by your model. This Pi over here is what you are modeling using this logistic regression model. But now you can use that to test the hypothesis of good fit, because the probability of succeeding, if the model is correct, can be written in this way. The expected value of y, if the model is correct, can be written in this way. And if the model is not correct, then the expected value of y will not follow your model. By the way, this is just a little bit of algebra with the speed function. You get that it's the same. So if my model is true, then the expected value will be like this. If my model is not true, then my expected value will be something else. But now I can use my data to test the null, because here you have, this is subject J in treatment I. Now, if he gets a 1, and I want to know, well, in total, how many successes I had in treatment I, what you do is you just calculate yi, right? The number of successes in group I is the sum of all the responses in that group, because every response is 0, 1. So if I sum all the responses in treatment I get my binomial variable yi. So yi is the number of successes I observe in treatment I. And how many failures I observe? Well, 1 minus, right? If you sum now 1 minus yij, we call that a OI0, we call that OI1, that will be the number, the observed number of failures in treatment I. And this will be the observed number of successes in treatment I. You can calculate that with the data, right? Now, if the null is true, if the null hypothesis is true, and this model actually is a good model, if my logistic model is capturing the main feature of the data, then how many successes I expect in treatment 1? You expect an I times pi head. Now this is the probability, this is what my model predicts will be the probability of success for treatment I. That's the prediction of my model. And if you multiply the predicted probability of success in treatment I by the sample size in treatment I, this will be the expected number of successes in group I. And this is the observed number of successes. So this is what your model predicts. This is reality. And now we can compare these two sense, right? By the way, what is the expected number of failures in group I? Well, that would be 1 minus the expected number of successes. That's why the probability of failing is 1 minus the probability of succeeding. And if you multiply that by ni, there it is. This is the expected probability of failure. This is what your model says. This is the amount of failures you may expect in that treatment. And this is the amount of success you may expect in that treatment if your model is correct. And you can write down the expected number of failures as ni minus the expected number of successes. And that's it. Now you can use the Pearson chi-square test, because the Pearson chi-square test essentially compares what you expect under your model with what you actually observe. And if these two things are very far from each other, then your model probably is wrong, because the model is expecting something that is very far from what happened. And if these two things are more or less equal, then your model, you have no reason to doubt your model. You have no evidence to reject the null. So essentially what you do is you calculate a chi-square distribution. And in a chi-square distribution, if you remember correctly, you compare the observed value with the expected value divided by the expected value, some kind of relative distance. That's what you do. You compute the relative distance between the expected values and the observed value. This is what you calculate, right? And you do a little bit of math because you're having this double sum here. Essentially, here it is. This is the chi-square distribution. And what you do is you calculate your response, which is binary. You subtract the expected value of the response under the model, right? That would be the expected value of the response under the model. And you divide by what would be the variance under the model. That will be the variance of a binomial distribution under the model. So you're essentially comparing the data to the prediction of your model. And you can prove that if n is fixed, so the amount of different values for your covariates is fixed, like in the dose study, in the animal experiment study, you can consider that you have only 20 doses. And if you include more animals in your study, you are not going to increase the doses because you specified. You're going to consider this, they are not 20 doses, they are 11 different doses because you increase the doses by 2. 0, 2, 4, 6, etc. So you have 20 doses, and these are the only doses you're willing to consider. Maybe due to biological reasoning, you know, it doesn't make any sense to increase the dose beyond 20 milligrams because it's going to be too much, right? So in that case, N is fixed. And if you increase the number of mice in your experiment, you decide now that in a state of 20, you're going to do this experiment with 50 mice. But you're going to still use this same 20 doses. You're not going to change that. So you need that assumption. And it's the same, for instance, if you use categorical predictors, and I'm considering gender and income, low and high, if I increase the sample sizes, my table is still a 2 by 2 table, because every new individual that I include is going to be a male or a female, and is going to have a low or high income. It's not going to change the possibilities for my covariance. So that's important. N needs to be fixed. If you have a study that when you increase the sample size, you increase the N, you increase the different numbers of observed covariance, that asymptotic doesn't work. So if N is fixed, and of course, if your model has less parameters than N, because in another case you have a saturated model, so if that is the case, and the sample size in every treatment goes to infinity, so you need to pay attention because there are several conditions here. In that case, your chi-square Pearson statistic follows a chi-square distribution with n minus p degrees of freedom. And now you can use this test to assess the goodness of fit of your model. So the Pearson chi-square statistic can be used when they are only categorical regressors, like I said, because if you have, for instance, gender and income, and you increase the sample size, you still have a 2 by 2 table. But I want to make a little bit of an observation here. You can also use it with continuous variable, but like in an experimental design, when you know that I will not use other doses, I'm going to use these specific doses, and if I repeat my experiment and I include more mice, it's fine, but the doses are going to stay the same. I will consider exactly these 11 doses. In that case, you can still use the Pearson chi-square. And then, like all Pearson chi-squares, you typically want to have the expected frequencies to be larger than 5, so that this predicted part here, this predicted expected values for the model, they tend to be higher than 5 to get some good asymptotic approximation. And none of them, of course, smaller than 1. Now, let's use this, for instance, with the mice data. I'm going to use it with the animal experiment data, and I'm going to use the logistic model first. And here you have, this is the way I program here, how you can apply the Pearson chi-square statistic. If you have another model, just make the obvious changes in the code and you get it. And here you have degrees of freedom 9. Why 9? Because it's n minus p. Now, what is n? Is the different values your covariate can take. We have those, and I can take 11 different doses from 0 until 20. That's why 11 over here. This is the number of possible outcomes for your covariates. How many different values you can have for x? You can have 11 values in this study, right? And p, what is p? It's the number of parameters in your model. And when you put those in your model, you consider it as a continuous variable in principle. So you have an intercept and a slope, 2 parameters. And that means you have 9. And are my conditions satisfied? Yes, they are. Because if I increase the sample size, the number of mice, the number of different values for those stay the same, they stay the same, because it's an experimental design. And as you can see, I get a p-value here of 0.80. And this was not for the logistic, this was for the log-log link. This is the link that got sharper to 0 and softer to 1. You get a p-value of 0.80. That model seems to be fitting the data very well. Now, what if I use the logic link? But if you use the logic link, here I have again the test. And again, you see that if you use the logic link, that was the original model, we fitted first. If you use the logic link, the p-value is again not significant. So both models seems to be okay. From the GOF, I don't get any evidence against the model. However, notice that indeed the logistic regression, the log-log link seems to produce a much larger p-value than the logistic regression. So it's, roughly speaking, I would say this model seems to give a better fit to the data than this one over here. But we will study that in more later on. But based only on this test, we don't have any evidence against the logistic model either. However, if I have to choose, we will see later more formal ways of doing this. I will go for the log-log link. Why? Because I saw it in the graph that it kind of goes to zero faster and it gets closer to the data points. And yeah, you need to ask a biologist, a toxicology, if it really makes sense in this case that the curve should go sharper to zero and then smoother to one. But it seems to have a higher p-value here. By the way, if you want to compare these two models, the model using the log-log link and the model using just the logistic link, you cannot use a test. You cannot use a likelihood ratio test, or you cannot use a wall test because these models are not nested. Don't forget that. Now, the deviance test, that's something rather new here. The deviance test, guys, is just it's a goodness of fit test. That's what it is. And it's completely analogous to the F-test we use in linear regression to check lack of fit. It's just essentially it's a likelihood ratio test. That's a deviance test. It's a likelihood ratio test. Now let's go back again to linear regression to remember what we were doing there. In linear regression, what you were doing is you have repeated measurements again. So for every value of the covariates, xi, you have several y's, right? You needed that in linear regression as well. So this is now the response of subject I in subject J in treatment I. And treatment I is given by this specific value of the covariates. And then you feed your model. And this is your linear regression model. And now you consider something called a saturated model. What is a saturated model? It's a model that for each treatment I, you let the treatment has its own mean, mu I. And this is the most general thing you can do. Every treatment has his own mean mu I. And that mu I doesn't need to be linear in variables. It's a completely general thing. And now this model fits the data perfectly. I'm not saying it's a good model. Not necessarily a model that fits the data perfectly is a good model. But essentially, you're comparing the saturated model with your linear model. And that's the F test for lack of fit. Logistic regression, the same story. Here you have the expected value on the logistic model. And here you have the saturated model. So what is pi I is the probability of success in treatment I. And what is treatment I is this specific value for the covariates. And now this pi doesn't need to be a speed function of certain covariates. It's a completely general parameter. That's a saturated model because that model fit the data perfectly. Now, when you estimate these PIs, you will get the observed proportions in every treatment. And what is a deviance test? You're going to compare your model, which is more parsimonious. You're going to compare your model with the saturated model. That's what you're going to do. And you're going to use the maximum likelihood. So the model under H1 allows for a unique probability for each predictor combination Xi for every treatment Si, and is usually referred as the saturated model. And that's it. That's it. What you have here is the log likelihood for the logistic model, for the regression model. This is the log likelihood. Go back to what we saw before. And you sum over n because this is the n treatments in your data. And a treatment is an specific value for the covariance. So here you have the log likelihood evaluated in the maximum likelihood estimator. And if you consider now the log likelihood without restrictions, just forget here you're putting this pi as the speed function of the linear predictor, and then you're maximizing that in beta. That's what you're doing there. But if you consider just the likelihood, and the pi is just as general probabilities with no further structure, they are not modeled by any other parameters, then what is the maximum of this log likelihood? It's just the observed proportions. You maximize the likelihood, not considering these probabilities functions or as functions of covariates. The maximum likelihood will be the observed proportions, and we call that the pi delta, the pi tilde, right? So this will be the saturated model. And then you calculate the likelihood ratio test, in which you compare the log likelihood of your model with the log likelihood of the best possible model, which is the saturated model. This is what your model can explain. This is what the saturated model can explain. And this is going to be negative. Why? Because the saturated model explains always more than any other model. It's not parsimonious. So this is going to be negative, but you have this minus over here, right? And this is just the likelihood ratio test. You are comparing your model, the fit of your model, with the fit of the saturated model. And this is the likelihood ratio test. And that's called the deviance test for goodness of fit. And under the same conditions, if n is fixed, and we talked about that already, and the sample size in every cell in your table or in every treatment goes to infinity, then the deviance test follows a chi-square distribution with n minus p degrees of freedom. And that's it. So it's typically useful when you have categorical regressors. Not always. If you have a continuous regressor, but like in an experimental setting, like those, you can use it. But you need to make sure that this n, the number of outcomes in your covariates, stay fixed. That's necessary. Even when you increase ni, this guy needs to stay fixed. That's a requirement. Okay, the deviance is essentially a generalization of the sum of a square of the errors in linear regression. When you see a deviance in ours, if you need to kind of make an association to understand what that is, a deviance is like what your model cannot explain. We're going to tell you more about it later. It's like the sum of a square of the error. So, and if you actually have, if you have a linear model, and you calculate the deviance, then you will see that you will get something equivalent to the sum of a square of the error. So if you use this deviance concept in linear regression, you basically get the sum of a square of the error, right? The deviance, of course, is always greater or equal than 0, because what you cannot explain is always typically positive, and it typically not 0, and it's 0 only when you are in the saturated model. Because in that case, it's like when you get another square of 1, all the points are on the line, just your model explains everything. Well, here is the same. A deviance of 0 means it's a perfect model. You can explain data without variation. I'm not saying that's a good thing to do, but that's what saturated models do. Now, let's visualize a little bit more what is the deviance and what is the null deviance, because I'll give you these two things. A deviance is essentially a likelihood ratio test. As I said, it's over here. The deviance, you compare your fitted model, the model you're using, with the saturated model. We call it here LS. So a deviance is a likelihood ratio test comparing your model with the perfect model. If the deviance test do not reject the null, that means that you don't need a saturated model. A more parsimonious model, the model you're fitting, is good enough, explains as much as the saturated model, but with less parameters. And then that's probably a better model. That's called the deviance. Now, you need sometimes a benchmark, because if you get a deviance with a number, well, is that good? Is that bad? And that benchmark is what we call the null deviance. And the null deviance is when you compared the best possible model, the saturated model over here, when you compare the best possible model with the worst possible model, right? That is what we call the null deviance. You are comparing the model that only has an intercept with the model that perfectly predict the data. And if you want, that's a little bit like the total sum of squares. It's everything you can explain. What is how much I have there to explain? Well, that's the difference between when you explain everything and you explain nothing. That's how much you can explain. That's the null deviance. It's the maximum thing that you can explain. The deviance, that's the null deviance. The deviance is the difference between your fitted model and your best model. So the null deviance is a generalization of the total sum of squares. The deviance is a generalization of the error sum of squares. Now, to show you this, let's use the deviance test. So I'm going to use it again with the animal experiment. Here you have the log-log link. And if you applied a deviance test, you get against 9 degrees of freedom, n minus p, n is 11 different doses, and you have 2 parameters in your model, it's 9, and you get this p-value for the log-log link. Again, if you use the deviance test, like with the Pearson chi-square test, you get no evidence against your model. And when you use it with the logistic model, again, you get no evidence, but you see that the p-value is substantially smaller. So everything together, it seems that this guy over here is doing a better job than this guy over here. And here I'm just showing you, for instance, the outcome you get when you use the log-log link. And as you can see here, you have the residual deviance. This residual deviance is just the difference. It's the likelihood ratio test comparing your model you're fitting with the best possible model. And you see this should be chi-square with 9 degrees of freedom, and you see that this is indeed not extremely far from 9, which is what you'd expect. If this is chi-square under the null, you should expect that it should be around 9. And what you have here then is the null deviance, that is the likelihood ratio test comparing the model that only has an intercept with the model that is saturated. And as you can see, it's 88. That's very far from 10. So that means you will reject the model that only has an intercept. If you compare the model that only has an intercept with a model that has a saturated model that explains everything, you have to reject the null model in this case. So this is everything that you can potentially explain, the total sum of a square. This is what your model doesn't explain. And you can see this is relatively very small compared with this. So you do have a good model. And then just to show you what we were saying before, I told you that the null deviance is the likelihood ratio test comparing the null model, the model that only has an intercept, with the saturated model. If you fit the model that only has an intercept, like here, then what is the null deviance? Well, the null deviance is always the same. Is when you compare the model that has only an intercept with the saturated model, you get there 88.98. And what is the residual deviance? Well, the residual deviance is the likelihood ratio test comparing your model with the saturated model. But your model now is just the intercept model, right? It's the one you chose over here. And that's why you get exactly the same values here. Because now these two things are doing the same. They are both comparing the intercept model with the saturated model. Why? Because this is the model you chose. You chose just a model with an intercept. It's just something I'm doing to illustrate you what the null deviance actually is doing. It's just comparing an intercept model with a saturated model. The residual deviance is comparing your model with a saturated model. All this is nice and well, but as I told you, you have this requirement that n, the total number of outcomes for the covariance, the different values you can get for the covariance, that n doesn't change when you increase the sample size. And this typically happens when you have categorical predictors, because then you just get an ANOVA table type. Factor A with A level, factor B with B level, you get an A times B table. And if you increase your sample size, individuals just get redistributed in the cells of the table, but the number of levels stay constant. Now, if you have continuous variables, well, if you are in an experiment, you can fix it, like in the animal experiment. But in another case, you don't have repeated observations. Every vector, every value for the vector of covariance is associated with only one individual. You cannot apply it in such a setting the chi-square or the deviance test. But there is another type of test that is called the Hosmer-Lemeshow test. And what this test does, well, guys, it just creates categories in the data. So what they did is you now calculate the fitted values for all the individuals. Now you don't have repeated measurements. So for every value of the covariance, you get one estimated probability. And what they did now, they created categories for these estimated probabilities. And they did that using two strategies. Here you have them. One strategy is you just consider G groups, and this G is arbitrary. You choose the G any way you want. And you consider, for instance, the n divided by G smallest predicted probability, right? The second group is the next n divided by G smallest fitted probability. And then the last group contains the largest probability. And this G is fixed, so now you have G groups. Whatever other individual comes, it will be classified in one of these categories. And strategy 2 is that they consider a group defined by all the individuals that have a predicted probability smaller than 1 over G. Second group, all the individuals that have a predicted probability between 1 over G and 2 over G, and so on. And the final group was all the individuals, group G, that have a predicted probability between these two values. And now you have G groups. And any new individual, you calculate the predicted probability and you classify it in one of these groups. So now you artificially created the categories, and then you use that to calculate the Pearson chi-square, the chi-square statistics. And now the chi-square statistic applied to these new categories is essentially the Hosmer-Lemshout test. Essentially is the same chi-square test, but now applied to a specific type of categories. And these categories are created in a kind of artificial way. Now, it's just a Pearson chi-square test. Now, they did a lot of simulations, and they show via simulation that asymptotically, this chi-square, so constructed, this Pearson chi-square statistics, actually approaches a chi-square distribution with G minus 2 degrees of freedom. That's what they found. And they also found that creating the categories using a strategy 2 give a better approximation than using a strategy 1. And this is the Hosmer-Lemshout test. It's not implemented in R, but here I'm giving you a function. It's very easy to implement this in R. Just copy and paste that function and you got it. Now, if you apply this to the donor data, because the donor data essentially you have continuous variables, you have age and you have gender, and is unique. You don't have, for every combination of age and gender, you have only one person that had that age and that gender, or maybe a couple of them, but not too many. So it's, you cannot apply the deviance and chi-square. But here you can definitely use the ideal situation to use the Hosmer-Lemshout test. And when you use it, surprise, surprise. By the way, G, the number of categories, is arbitrary. You can consider 5 or you can consider. The standard thing is to consider 10. The default in this function is 10, but it's arbitrary. It's like using 5% for a p-value. But surprise, surprise, when you fit the model, this is the probability you get. It's significant. So this model over here seems to be missing something in the data. I mean, is this too bad, too serious? Well, we are going to check it now, but it seems we're missing something in this model, some characteristic in the data that we are really missing. But now, okay, suppose that you are like in the donor data, you do the GOF test and it's significant. I'm missing something in my model. My model is not capturing the main feature of the data. But now how I proceed from there? What is the problem? What I have to change? And for that, you have the diagnostic tools like the residuals, right? The same way you have residuals in linear regression, you have residuals also in logistic regression. And the residuals are useful because they help you to see what exactly the problem is. You do the GOF, if you don't reject, you're kind of happy with your model, you can go further. But if you reject, that means you're missing something in your model. Now the next question is what I need to change. And there is when the residual analysis can help. Now, essentially, you have a logistic regression model. We are going to keep the repeated measurement setting. You have the logistic regression model, the systematic part of the model. You just model the probability of having an event, of observing an event. Sorry, here we're using a Bernoulli distribution, not a binomial, but it's the same. So here you're modeling the probability of having an event as a function of the linear, as a linear function of the predictor, and you're using a logic link. That's the systematic part of the model. The distribution part, then how my responses vary around this mean over here. Well, you are using a Bernoulli distribution, right? Now, you can write this model. This is your model. This is your logistic regression model. This combined with this. You can write the model like in a normal linear regression model. Essentially, you're modeling the expected value. So here you have your response, which now is 0, 1, and you can write that as the expected value plus the residual. You can do that. And really, with a binary response, it looks strange, yes, but the thing is that the expected value, pi, that is the probability that you will get a 1. So the error term now is like in linear regression. It's yi minus the expected value, right? That's the way you did it in linear regression. In linear regression, the residual term, not the error term, the residual will be when we estimate the probability. The error term in linear regression is your response minus what your models predict. That is the residual term in linear regression. That's the epsilon, right? The only difference that now the residuals can only, this error term, sorry, residual is when you put here the estimator for pi, that would be the residual. These error terms can only take 2 values. If y is 1, now the residual is 1 minus pi. And then this cancel out with the pi and you get the 1. And if y is 0, then the error term is minus pi. But you can write your model. You can write your logistic regression model or probit model, whatever you want. Well, in this case, we're dealing with the logistic regression. You can write it in this way. The only weird thing is that now the error terms can only take two values, 1 minus pi or minus pi. But you can do it. And you can write the error terms just like you did in linear regression, in this way. Now, what is the residual? It's like in linear regression. It's your response minus the predicted value of your model. The fitted value, we call it linear regression. So this is what your model predicts. You're estimating here. That's why I call now the residuals. These were the errors because you have here the true pi. Now, once you estimate it, this pi, you get the residuals. We call it EI. So EI is just the responses minus the estimated model. But again, that can take only two values. 1 minus pi I hat or minus pi I hat, depending if y is 1 and 0. But you can do the same as in linear regression. This is exactly the same definition. It's exactly the same definition of residual we use in linear regression. That's why I told you these models are different, but the structure is very similar. In linear regression, what you have for residuals was, this is very difficult, the residual was linear regression y minus x times beta hat, right? Or if you want, in linear regression, the residuals were y minus the estimated mean value. That's it. That was in linear regression. But now this estimated mean value is a probability. But it's the same. This is the same as this. And now we know from linear regression that the residuals themselves are not homoscedastic even if the model is homoscedastic, and you typically divide by the standard error of the residual. The same here. We did it in ANOVA. So that's the Pearson residuals. What is the Pearson residuals? This is the ordinary residuals, the ones you're using before, but now you divide it by the estimated standard error of y. And what is the estimated standard error of y? Y is Bernoulli. So the variance of a Bernoulli is pi times 1 minus pi. The standard error, you calculate the root square of that. And this is called the Pearson residuals. That's it. Now, if you look at this, you will see that the Pearson chi-square, what is the Pearson chi-square? It's just the sum of the square of the Pearson residuals. You get this immediate relationship between the Pearson residuals and the Pearson chi-square. Now, the sum of the square of the Pearson residuals equal the Pearson chi-square, a statistic that, remember, is a measure of lack of fit. So, the square of the Pearson residuals measure the contribution of each observation, of each binary observation to the Pearson chi-square. So if you rejected the null, that means that your Pearson chi-square test was very large. And then the Pearson residuals may help you to see which individuals were contributing to this lack of fit. That's what it does. Now you need to be careful because this doesn't follow a chi-square distribution unless you have repeated measurements. So if you do not have repeat of measurement, you can still use this in a kind of informal way. So if you don't have repeated measurement, this is not chi-square distributed under the null. But you can still informally see, well, I know that if this is large, that is signal, that's evidence of lack of fit. I cannot use a chi-square distribution anymore, but I know large chi-square, Pearson chi-square test, large values are giving me evidence of lack of fit. And now through the Pearson residuals, I can see more or less what are the values, the observations that are contributing to the lack of fit. But in general, it's important to know that if you don't have repeated measurement, the interpretation of this needs to be careful. Now, like in linear regression, like in ANOVA, you remember the semi-studentized residuals, and then we have the studentized residual. And that comes from the fact that these semi-studentized residual, they don't have variance 1. Because you are estimating the pi here, right? You're not putting the true value. So this guy does not have variance 1. You need to take into account that you're not divided by the true variance, but by an estimated value of the variance. And that produced in ANOVA the so-called studentized residuals. What you actually do is you take into account the leverage. You remember we also saw that in ANOVA. And here we do exactly the same. So the Pearson residuals do not have unit variance. Why? Because you are estimating, you are plugging in there not the variance, but an estimated of the value. So a better procedure is to divide not by the standard deviation of y, but by an estimator of, taking into account that you are estimating that variance as well. And this is what you do over here. You use the leverage that we studied before. So what you do is you consider the hat matrix. In logistic regression, you can see that it follows a very similar pattern as the one of linear regression. And then you divide not the sum of this leverage is equal to pi. And then you divide now the row residuals not by the estimated variance of the yi's, but you also divide it by their estimated standard deviation, the real one, taking into account that you're estimating the pi. And you can show that this is just the Pearson residuals now divided by this term here. And these are the student-assigned Pearson residuals. Guys, this is exactly the same as in ANOVA, the student-assigned residuals in ANOVA. So the ordinary residuals can be made more comparable by using these student-assigned Pearson residuals. And now they will have variance 1. I need to make a little note. If you have repeated measurements, like when you use a binomial distribution, not a Bernoulli, but like a binomial, like when you have all the covariates categorical, or you have a continuous variable, but the number of doses is fixed, like in the animal experiment. When you have that, then if the sample sizes are large, you can show that the studentized Pearson residuals they follow approximately a standard normal distribution. Because now you are using really the correct denominator when you construct them. And the advantage of that is that if they follow a standard normal distribution and you made a plot of the student-assigned Pearson residuals, then you know that any residual that is larger than 2 or larger than 3, they really show lack of fit. Now you have a cutoff point. If I make my plot of the student-assigned residual, anything above 2 or above 3, minus 2 or minus 3 is giving me evidence of lack of fit. If you don't have repeated measurements, you can still plot them, but the interpretation becomes difficult because they are not normally distributed. You know that they are contributing to the chi-squared test statistic, but the chi-squared test statistic is not chi-square distributed. So the interpretation becomes a little bit harder. You need to use them in an informal way. What about the deviance residuals? But it's a little bit of the same idea. Remember, the model deviance is just a likelihood ratio test, where you are comparing your logistic regression model with a saturated model. That's it. And I gave you the expression for group data, for repeated measurements. Now, suppose that you don't consider your repeated measurements, or you don't have them, then you can show that when you do not have repeated observations, like for instance, when you have continuous covariates, then how many different values you have for your covariates, as many as individuals in your study. How many repeated measurements for every level of your covariate? 1. It's unique now. And then y is equal to j, and then this pi tilde is just going to be the response, because now every vector of covariate, every value of that vector is associated with one and only one person. And then you can construct the deviance test. It's going to be like here. Now, this deviance test is not going to have a chi-square distribution anymore, but then you can see what is the contribution of one individual to that deviance. You calculate the root square of that contribution, and you put the sign of yi minus ni, and then the estimator, the expected value. And this thing over here is what we call the deviance. Just don't forget that this ni is 1 now. This is the deviance residual. And again, if you sum the squares of the deviance residuals, you get the deviance test. So again, in this case, the square of each deviance residual tells you the contribution of that observations to the deviance test. And you know that a large value of this guy is showing you lack of fit. So if you see how much every subject contributes to this, it may help you to see which subjects may be causing, of which group of subjects may be inducing lack of fit. But again, remember, if you don't have repeated measurements, this D doesn't follow a chi-square distribution, so it's difficult to interpret It's just something you have to use with some kind of exploratory fashion. Now, how do you use this residual? Well, like in linear regression, you can plot these residuals against, for instance, the linear predictor, or you can plot these residuals against a covariate. You decide. You can be creative. You plot the residuals against different things, and then you analyze the pattern. Let me show you, for instance, for the donor party data, because there we saw that we have some lack of fit. The model is not fitting the data well. Now, remember, if the model is correct, if this model you're using is correct, then the expected value of the responses is pi, because it's a binary response, right? And that means that if the model is correct, the expected value of the difference between reality and what your model predicts, so the expected value of the residuals, that should be approximately 0. If the model is correctly specified, then your model should be predicting something close to reality. So typically what you do is you plot the residuals against the linear predictors. So for every individual, you have a unique value of the covariates, and that times beta is the linear predictor. So now you plot for every individual the linear predictor and then the residual. And then you calculate the lowest smooth. What you do that is you try to see, so here you have the residual plot, and you may notice this weird structure that I have just two curves here for the residuals. That come from the fact that the residuals now can only take two values. You remember, if you go back to your definition of the residuals, if you go back there you see that you can only, the residuals now can only have two values, 1 minus pi head of minus pi head. And that's the reason why you get only two possible lines here. These are, for every value of the linear predictors, you may only get one of these two values, depending if the response was 0 or 1. And that makes the whole thing difficult to interpret. Now, I know that as an average, these residuals should be close to 0. And how you calculate an average of these things? You calculate this lowest smooth curve. Here you have the 0 line over here. You have the 0 line over here. And here you have the confidence bands, the confidence intervals for this residual line. And as you can see, well, that seems to be around 0. Sometimes over here, it goes a little bit above 0. But essentially, if I look at the confidence lines, yeah, the line 0, the 0 line lies nicely inside the confidence interval. So from this plot, I don't see any problem. And this is for the deviance residual, the previous was for the chi-square residuals. I don't see any problem either. But look at this now. Now I plotted the residuals against age. And now I see that I get a problem. I get a problem because around an age of 10 over here, now my confidence interval is above 0. The curve is above 0. So there seems to be missing something with the covariate age now. And I know the model has a problem of lack of fit, so it seems to be, maybe I need a quadratic function of age and not just a linear function of age in my model. That's what this is indicating. And well, these are the code just to get the residuals. And the other code, you need to go through that yourself. And another way of seeing that, what I did here, you have the data. This is the zeros and the ones. This is just the data, not residuals. And you may say, wait a minute, why you have several points here if this should be just a line of ones? That's something I did it artificially. I jittered the data just to show you that there are more points here. And now I fitted the lowest curve as well. And when I do that, I see what I have here is the survival. I jitter it, you know, the 0, 1. I get this quadratic term. I get this quadratic type of shape. And the model I'm fitting is just a model that goes like this. The model goes continuously towards 0. And if I look at this is the model we are fitting now. The model we are fitting now goes to 0 like this. That's my fitted model. And when I look at the lowest, I see this quadratic pattern. Now, think about it. It makes a lot of sense to have a quadratic pattern, a quadratic function of age. Why? Because when you are very little, when you are a baby or something, I expect that your probability of surviving are smaller because babies are really, really vulnerable. Now, when you are very old, I guess your probability of dying, of surviving also is going sharply to zero. But if you increase age to a certain moment, you are dealing with a stronger person. So 10 years old is stronger than a 1-year-old. A 15-year-old is probably stronger than a 10-year-old. So I could expect the probability of surviving increasing with age to certain moment, to certain point. And after a certain point, getting old hurts you, right? To a certain moment, before that, getting old makes you stronger until you reach your peak, your physical peak. And after a certain age, I expect that, you know, the probability of surviving start decreasing. So I may indeed need a survival. I may need a parabolic model, a kind of quadratic model. Now I plotted the curves for men and for males and females, and I see this quadratic pattern for both males and females. However, it seems to be much more pronounced for females than for males. For males, I would say you can kind of go along with just a decreasing model. Doesn't seem to change so much, but for some reason, for female, you really see this very pronounced parabolic effect. So, and here you have it. So what you have here is what we have here. This is the, I create intervals of age. This is between 1 and 10 years, between 10 and 25 years, and between 25 and 70 years. And these are the observed probability of survival for males. Over here, the reality, the observed one. And this is the one that the additive model predict. And you can see that the model is predicting pretty well for 1 till 10. Is predicting not that bad between 10 and 25. There are more cases than what the model predict. The probability here is a little bit higher. That's the parabolic effect, right? It's a little bit higher, but still not that much of a difference with the predicted value. Remember that these are estimated values. This is not a true. And then between 25 and 70, the probability of survival goes down sharply. And this is the observed value, and this is the predicted value of the model. So for males, we are doing fine. So a kind of decreasing relationship between age and survival seems to be reasonable for males. Now, if you look at females, the situation is different. Because for young girls between 1 and 10, your model is overestimating the survival probability, 10% more. Now, between 10 and 25, your model is underestimating the probability of survival, because here is 100%, all of them survive, and your model is predicting a 70% survival. And for older people, again, here your model is overestimating a little bit the survival probability. So here your model predicts, the prediction of your model for female is a continuous decrease. That's what you see in this side. Whereas reality seems to indicate a parabolic effect, something like this, goes up and down. And my model is predicting something like this, constantly going down. And for males, it's the same, but for males, it's really like the parabolic effect a little bit alone, whereas the model is describing a going down. These two seems to be quite of the same, but here we are clearly having a problem. So this is what my model predicts it should happen, but we saw that this is what my model predicts it should happen, but we saw that this is what is actually happening. And there is a problem, and I get a lack of it. So fine, I'm having a problem, and we will see later on how to correct it. Before that, I'm going to give you another 2 diagnostic tools. These 2 diagnostic tools, I mean, when you have fitted your model, you want to detect problems. And we have seen different things. We have seen the Pearson chi-square test, it's a GOF test. We have seen the deviance test, it's a GOF test. But there are other things that you may want to consider. And this other thing is, for instance, you want to consider the influence of certain observation on the chi-square and deviance test. We call that influential observations. And a way of doing that is you can calculate the difference between the chi-square test when you use the entire data set and the chi-square test you will get if you omit observation I. So it's called the ith delta chi-square statistics, and it's defined as the difference between the general chi-square when every data point is considered, and the chi-square you will get if you omit one observation. And that will tell you to a certain degree how influential that I observation is. Because if this guy is a huge reduction, then this observation is changing the chi-square dramatically, right? And for the deviance test, is the same. The delta deviance is just the difference between the general deviance test you're getting here with the deviance test you will get if you omit the I observation. And if this delta di is very large, then this I observation here is having a huge impact on your deviance test. Now, you need to take into account that how many delta chi-square and delta deviance you need to calculate. You need to calculate one per observation, right? For every observation, you need to calculate the deviance of the data without that observation. This one, you do it one time. This is the general chi-square test, general deviance. But then you need to calculate, remove observation 1, calculate this. Remove observation 2, calculate this. You need to calculate n times the deviance and the chi-square. You need to fit the model n time. Now, that means that you need to do n maximizations of the likelihood, but to calculate the deviance or to calculate the deviance and likelihood ratio test, or to calculate the chi-square, you need to calculate the maximum likelihood estimator. So you need to maximize the likelihood n times. And if you have a large data set, this is going to be very costly computationally. So there are certain approximations to these delta chi-square and delta deviance. There are some approximations, and you can show that a good approximation for the delta chi-square is just the square of the studentized Pearson residuals. And then you don't need to fit the model n times anymore. So these are approximations. It's not the exact value, but they are computationally more affordable. And for the data deviance statistics, what you do is you calculate the deviance residual, or the deviance residual, then times, this is the leverage times, the estimated leverage times the square of the studentized Pearson residuals. As I said, these are practical solutions that people have found to avoid these n maximizations of the likelihood, because it's very costly to do that computationally. If you have 5,000 individuals, or if you have 1 million individuals in your data set, I don't know, and you have rather complicated model and you have to refit that model 50,000 times, is going to be costly. So in summary, this delta chi-square and this delta deviance give the chance of the change, in the Pearson chi-square statistic and in the Pearson and in the deviance statistics, respectively, when you remove one observation. And that allows you to quantify how big is the impact, how much I reduce my lack of fit if I remove one observation. So it provides some kind of measurement of the influence of certain observation. But again, keep in mind that if you don't have repeated measurements, this chi-square test, Pearson chi-square test, and this deviance test, they are not anymore chi-square distributed. So this delta chi-square and delta deviance is difficult to interpret, because you cannot put a cutoff to say if the delta chi-square is larger than this, then this is an influential observation. You cannot do that if you don't have repeated measurements. And the same with the studentized Pearson residuals. If you have repeated measurement, you know the studentized Pearson residuals, when the sample size is large in each treatment, then you know that they are going to be approximately standard normal. So you know that a Pearson, studentized Pearson residuals larger than 2 or smaller than -2 probably reflects some kind of problematic observation. But if you don't have repeated measurements, they are not normally distributed, so you don't have a cutoff point. I get a Pearson studentized residual of -4. Is that an influential observation or not? It's difficult. The same with the delta chi-square and delta deviance. But you use them in an exploratory way. So again, this is what I have just said. Interpretation is not simple, because the distribution of these statistics is unknown. So you cannot define like a cutoff value to identify the influential observation. It's difficult. So what you can do is, well, people plot these things, for instance, against the identifier of the subject, right? the number case. And, or for instance, you can plot them against the estimator of the linear predictor. And then you look and you subjectively evaluate that graph. You try to, if you get like peaks in your spikes in your graph, then you know that probably that points there that are above all the rest may be problematic. Let me show you a simple example so that you can see it here. This is for the donor party data. So what we have here is this delta chi-square. And this is it. You get here these values. For instance, I don't know, it's difficult to put a cutoff. I mean, you could say, well, here I have 2, but this is completely arbitrary. I see like 2 levels here. I have these guys over here that seems to be very far from the rest, and then I have these 2 over here that also seems to be larger than the rest, and the rest, they all seems to be under 2, between 0 and 2. So this is, does that mean that these guys here are influential? Difficult to say, because we don't know, we don't have a cutoff, but you may want to remove them and feed the data again and see what happened. But these guys are contributing substantially to the chi-square statistics for lack of it. But in the donor part of the data, that chi-square statistic doesn't follow chi-square distribution. So it's difficult, guys. It's not like a linear regression. It's a little bit more difficult, but you use them in a kind of exploratory way. And here you have for the delta deviance. And again, here you see most of them, well, here you have 2.5, most of them, the mass of the values are lying in this band. So these again are the potential influential observations. You may want to remove them, see, fit the data, see what happened. But if there is lack of it, this one of these guys may be the culprit. Maybe you need to refit the model, try to test again and see what happened. Now, another thing you may want to see, because all these residuals, the Pearson residuals, the studentized Pearson residuals, the delta chi-square residuals, if you want, the delta deviance, all these are telling you lack of it, in the sense of, yeah, these are the tests we are using to reject the null hypothesis that the model is fitting, and we are calculating how every observation contribute to that test, made that test worse. Now, another thing is like you may want to see the influence of an observation on the linear predictors themselves, right? If I have this in this linear function of the predictors. So if I remove an observation, how much that will change the eta, the linear predictor itself. And that is what we in regression, you call that is the Cook's distance, is the one used in regression. And even though it may be less useful in logistic regression, is still something you want to use. For a standard regression model, this Cook distance give you an assessment of the standardized change, let's say in the fitted response vector, when you delete one case. Here is not going to be in the fitted response vector because, well, not directly, because you have this nonlinear function, the nonlinear response functions relating the probability with the linear predictor. It's a little bit more complicated, but in logistic regression, what it will give you is the standardized change in the linear predictor themselves, if you remove certain value. And you can show that, well, an approximation to this Cook's distance in linear regression is given here. And as you can see, it depends on the same sense. The Pearson residuals over here, the leverage over here, and then the number of parameters in the linear predictor, the number of betas. And this is just giving you this Cook's distance. Again, how to interpret that? You just made the plot against the number of cases. That's what we did until now. We always plotted these things against the number of cases. And you know, these are going to be the observations that if you delete them, you're going to get a substantial change in the linear predictor. And you may want to play with that. You may compare this with the other plots we saw. And I think that, for instance, there are some values, all of them kind of come back again and again. This 55, 64. If you look at, for instance, here you have the deviance residuals, the delta deviance, you see again this 55, 64, this 6 over here. If you now use the delta chi-square statistic, you see again this 55, this is the 4. So these are observations that somehow, you know, they pump out of the rest of the data, and you may want to have a look at them. You may want to just see if these observations, if when you remove them, you get kind of a different thing. So this is what you do. This is the delta chi. By the way, wait a minute. Let me go a little bit back. So this is it. Now, what I'm going to do now is I'm going to fit my quadratic model. for this donor party data, because when I started playing with the residuals, the variance residuals, I saw that if I plot it as a function of age, then the average residual is not 0 anymore. And when I made this plot that I plot the responses against age and I use this lowest, I saw that there is also like a quadratic effect. And then when you think about the problem, you realize that it may be indeed the true that I need a quadratic effect, because babies are very vulnerable. When age increase, they get older. You are dealing now with more robust individuals. Their chances of surviving should increase with age, but after a certain point, the chances of survival should decrease with age. Now, the interesting thing here is that when we did that for females and males, that pattern, that parabolic pattern, seems to be a lot stronger for females. For males, you see this parabolic effect, but it's a lot smaller. It kind of goes down nicely, but for females, you have this parabolic pattern. So what I did here is I did fit a parabolic model. And as you see here, I made an interaction with gender, because this parabola seems to be different for males and females. By the way, you may ask yourself why I use here this poly function in R. This is just to use to try to reduce the natural collinearity you get when you use quadratic models or polynomial models. It's like you construct orthogonal quadratic models. But guys, go to Google, find the details, but it's essentially a parabolic model. So as you can see here, this will be the model for males. So for males, what you get for males is that the fem is 0. Remember that the asterisk here means main effect plus interaction, so you don't have the interaction. So this is the intercept, this is the linear effect for males, and this is the parabolic term for males. And then for females, you just need to plug in there fem equal to 1. Now, when I compare these two models, when I compare the linear model using the likelihood ratio test, that's what I'm doing here. If you compare the linear model with the quadratic model, they are nested because a linear model is a special case of a quadratic model, you get a very highly significant p-value. So we do seem to have these parabolic effects there. It's not just some kind of artificial thing. It seems that the model becomes much better when you consider this parabolic effect. Now, I'm introducing this parabolic effect not because, oh yeah, okay, why we don't introduce a parabolic effect, or why not a cubic effect, or why not a fifth degree polynomial? That's not a way of doing a statistic. But when I look at the data and I see this parabolic effect, I do get it, that people may get more robust to certain age, and after that, they become weaker again. So we are vulnerable mostly at two periods in our life, at the beginning and at the end. And then in the middle, when we are just in our peak of life, then we are strongest, right? That makes sense to add this parabolic effect. And I now try to check the goodness of it using the Hosmer-Lemshow test, and now with the parabolic model. And when I do that, the lack of it disappears. The lack of it disappears. So that was apparently, and I get a very non-significant p-value, 0.87, almost 0.88. So that was the problem, guys. The probability of survival is not just like monotonically decreasing with age. The probability of survival increases with age until a certain moment, and then it goes down after a certain moment. And that parabolic effect seems to be more pronounced for women than for men for some reason. And now, if you compare again the observed probabilities with the predicted probabilities, so this is for males between 1 and 10 years, between 10 and 25, and between 25 and 10. This is what you observe, the proportion of survivals in these categories. And this is what your model predict. And as you can see, for males, you still get this kind of decreasing. The model still predict this decreasing pattern, but that's pretty much in agreement with the data. Here you have 56% of survival, observed survival. Your model predicts 0.53. 58 over here, 51 over here. 32, 37. So for males, the model seems to be capturing the main features. Now, the disaster was with female. There, my model really missed it. And now with the parabolic model, I do get better results, because now my model is really capturing the main feature. So women's, the probability For the between 1 and 10, you see that it's 0.69 as the observed. My model predicts 0.69. It's a very good prediction. Between 10 and 25, all women survive. That's what data says. Of course, the model is not going to say that all survive, because actually that may just be an overfitting. But you see that your model is predicting a 95% chances now. It's increasing. It's not constantly decreasing. Now my model is saying from 1 until 25, it seems to be increasing. And then you see that after 25, between 25 and 70, the probability of surviving decreases for women. 40%, your model predicts 46. So now my model is really capturing this pattern over here, and I don't have lack of it anymore. So it seems that is it. You need that parabolic effect. And when you made this delta chi-square now, you see that only now one value pumps up here. This is observation 24. You may want to go there and have a look at it. And when you do the other plots, well, you get this 24 pumping up. I didn't do the exercise of deleting and fitting the model again, but I mean, I was happy already because I didn't have any lack of it in my chi-square, in my Lenshout test. I have a very high p-value, 0.80, and when I compare my model with the observed probability, was very good. So I really didn't go so much so much deeper into it. And guys, this is now the new prediction. Of course, we are talking about parabolic effect. Probably these parabolic effects are also an approximation of reality, but it seems to be good enough. So here you have the situation. For males, you get like this constant decrease over here. The probability of surviving seems to go down with age systematically. For men, there is a little increase over here, but it's minimum. For females, for some reason, you have this very strong parabolic effect. They improve dramatically their survival probability between 0 and, let's say, the peak over here seems to be reached about 18 years old. And after that, their probability of survival seems to decrease dramatically. I don't have a clear explanation for that. If there is one, I don't have it. If this is because men were protecting women, somehow they seems to protect them from when they are babies or small until, let's say until 40, and after that somehow they didn't protect them anymore. I don't know what that is. I don't know how to interpret this. There may be some biological difference in the way women evolve with age that explain this parabolic effect for women and not for males. If some of you have a nice idea to explain this, send me an email, because I really don't know, but it seems to be the way the data behave. So just 1 minute more to tell you a summary. The residuals and diagnostic tools in logistic regressions are clearly a lot more tricky than in linear regression. It's just because we have less information, right? A binary outcome has a lot of less information than a continuous outcome, but it's equally relevant to check it, to check the lack of fit, to make this test, to try to check if you have influential observations, etc., is equally important. The impact of an individual observation or a couple of observations in logistic regression seems to be minimal, actually, because you have this logic link of this profit mean. It typically tends to be robust, but you need to check it anyway. So the chance that that one single observation will have like a huge impact in the fit is really very small in these cases. And yeah, if you have an influential observation, if you detect one, it may or may not be appropriate to change the model. That's something you need to discuss, but you should at least understand that I have some influential observation. I may fit the model with them, without them. Like in this case, in the donor party data, we detected some lack of fit. Should I change my model, or shouldn't I? Or I shouldn't? What is the right thing to do is not always clear. In this case, I changed it because when I started thinking about it, I realized that it just made sense to consider a parabolic model. It made sense to think that very young people, like babies, and very old people have less chance than people that are in adulthood. And that's why I consider this parabolic effect. It has some kind of weird part to it, that is that the parabolic effect seems to be more pronounced for males than females, and I don't know why that's the case. But I didn't change my model just by changing it, but because it makes scientific sense to change that. So guys, that's it for today. I hope this help you in the future when you're fitting this type of models to kind of do this model checking, which is an extremely important part. Remember that the model is never going to be perfect, but it needs to be a good approximation, and we need to make sure that is the case. So I will see you then next Wednesday, and there we're going to discuss a very specific issue with logistic regression that is called quasi or complete separation. And it's something that do happen in practice, and it can give you some kind of very weird results. But I will discuss that with you next Wednesday. Thank you for being here today, and I will see you again.